Have you ever wondered how people explained the world before science? Not before telescopes. Not before Einstein, but before we even thought to ask a question and test it. Before science was a word, humans looked up at the stars and told stories. A thunderstorm wasn't just weather, it was the wrath of Zeus. An eclipse, a demon devouring the sun. The changing seasons, gods arguing, lovers separating, the earth grieving. These weren't metaphors. They were explanations, and for thousands of years, they were enough. Because when your child is dying of fever, or your crops have failed for the third year in a row, you don't want statistics. You want meaning. You want to know why something happened. Not just what happened. That's the mind we started with. And honestly, it worked for a while. See, the human brain isn't built for objective truth. It's built for survival. And stories, especially emotionally satisfying stories, keep groups together, help you predict danger, and pass down knowledge in a way people remember. You can't give a 5-year-old a chart on lunar cycles, but you can tell them a tale about the moon being hunted by a wolf. And suddenly, they never forget what an eclipse is. So we traded precision for meaning, accuracy for memory, truth for trust, and most of the time, it was close enough. But here's the problem. Stories are emotionally persuasive, and that makes them dangerous. Because once a story fits, once it feels true, we stop questioning it. If something burns, it must be angry. If something floats, it must be pure. If something falls, it wants to return to earth, not tested, not measured, just felt. And so early humans built entire models of reality based on what seemed natural, not what was provable. This is what scientists today call intuitive physics. And the truth is, you still use it. Every day, you still expect heavier things to fall faster. You still think constant motion needs constant force. You still get surprised when a plane lifts off. Or when a bowling ball and a feather hit the ground together in a vacuum at the exact same time. You're not dumb, you're human. The pre-scientific mind never really left. It just put on a lab coat. Now imagine living in a world where everything was explained this way. No equations, no instruments, no controlled variables, just tradition, just stories, just the elders saying, this is how it's always been. And that's what makes what came next so radical. Not just that we started doing experiments, but that we dared to question stories. We began to say, what if the gods are wrong? What if fire doesn't want to rise? What if the moon doesn't care? That shift, from stories to skepticism, is where physics truly begins. In the next part, we meet the man who turned these early beliefs into a full worldview and accidentally trapped humanity in intellectual cement for almost 2,000 years. His name was Aristotle, and for a very long time, he was the final word on how the universe works. Ready to go deeper? Let's continue. Aristotle's physics, a universe with purpose, not laws. You might think of Aristotle as a philosopher, but for over 1,500 years, he was the authority on physics. When people in medieval Europe wanted to understand motion, space, or the stars, they didn't do an experiment, they asked Aristotle. And why not? He was brilliant, persuasive, and gave the kind of explanations that felt complete. Not mathematical, not predictive, but satisfying. Here's how Aristotle saw the universe. Everything was made of 4 elements: earth, water, air, and fire. Each element had a natural place, and motion was just things trying to get back where they belong. So a rock falls because it wants to return to earth. Smoke rises because fire belongs near the heavens. Water settles because it belongs between earth and air. Simple, right? And in a way, it actually fits a lot of everyday experience. Drop a feather and a stone. The stone falls faster. Push a cart, it rolls for a bit, then stops. Heavy things sink, light things float. That's the genius of Aristotle's physics. It agrees with your intuition, but he didn't stop there. Aristotle believed every object, every being, had something called telos, its purpose, its end goal. A seed becomes a tree, a child becomes an adult, a rock falls to the ground, all because it's in their nature to do so, not because of invisible forces, not because of numbers, but because of inherent purpose. In his view, the universe wasn't governed by laws. It was driven by meaning. Motion wasn't the result of pushes and pulls. It was a fulfillment of destiny, and that, to a deeply human brain, makes more sense than gravity ever could. Now imagine living in that worldview. You're not measuring velocity or acceleration. You're asking, what does this object want? What is its nature? What is it meant to do? It's elegant, it's poetic, and it's utterly wrong. But here's the catch: nobody questioned it, because Aristotle wasn't just a thinker. He was the thinker. His ideas were so influential, they became doctrine. For centuries, European scholars weren't taught how to reason. They were taught what Aristotle had already reasoned. And since his physics matched what people saw with their own eyes, it felt like truth, until someone dared to measure it more carefully. But before we go there, let's be fair. Aristotle wasn't stupid. He was ahead of his time. He noticed that objects stopped moving unless pushed. Because in his world, there was no idea of frictionless motion. He saw heavier objects fall faster. Because in air, they do. And without equations, clocks, or airless chambers. How could he know any different? He was using the tools available: logic, language, and observation. But he made one fatal error. He believed that if something makes logical sense, it must be true. That's why Aristotle's physics endured for so long, because it wasn't just descriptive. It was philosophically complete. You weren't just studying how things moved. You were studying what they meant. The universe wasn't a machine, it was a story. And Aristotle was its narrator, but that comfort came at a cost. For nearly 2,000 years, physics became less about discovery and more about confirmation. Experiments were rare, doubt was discouraged, and progress stood still. Until, slowly, cracks began to form. In the next part, we meet the early rebels, thinkers from the Islamic world and Byzantine Empire, who quietly began to challenge Aristotle with something far more dangerous than logic: evidence. Cracks in the wall, medieval and Islamic challenges to authority. For nearly 2,000 years, Aristotle's physics stood like a fortress. Unchallenged, undefeated, a worldview so comprehensive, it seemed absurd to question it. But behind the walls of medieval Europe, in places where science wasn't yet called science, cracks had already begun to form. They didn't start with revolutions. They started with questions. And some of the earliest came, not from Europe, but from the Islamic Golden Age. Around the 10th and 11th centuries, a brilliant network of scholars began to do something quietly radical. They read Aristotle and then disagreed with him, not blindly, not emotionally, but logically, and with growing curiosity, experimentally. One of the first major figures, Ibn al-Haytham, also known in the West as al-Hazan, born in what's now Iraq, around the year 965. He wasn't just a philosopher, he was a scientist before the word existed. His work on optics challenged Aristotle's claim that the eye sends out rays to see the world. Instead, al-Hazan proposed the exact opposite, that light travels into the eye. And he didn't just speculate, he tested it. He built camera obscuras. He isolated light beams. He measured angles of reflection and refraction. He was doing something new, experimenting to learn, not just reasoning to confirm. That alone was revolutionary. Then came Abu al-Barakat al-Baghdadi, a 12th century scholar who challenged Aristotle's idea of motion. Aristotle claimed that for something to keep moving, it needs a constant push. But al-Barakat suggested something far more modern. Once an object is set in motion, it can continue, even without a mover. That sounds obvious now. But at the time, it was a dangerous idea. It hinted at a concept the world wasn't ready for. Inertia, the same idea Newton would formalize centuries later. Even in Byzantine thought, you find early stirrings of resistance. A thinker named John Philoponus, in the 6th century, argued against Aristotle's falling body theory. Aristotle said, heavier things fall faster, but Philoponus suspected, maybe they don't. He proposed an early version of what Galileo would later prove: that all objects fall at the same rate, regardless of mass. Unless something interferes, like air resistance. No telescope, no stopwatch. Just reasoning, refined by doubt. But here's the problem. None of these thinkers broke the fortress. Why? Because they weren't operating in a world that welcomed doubt. Their writings were rarely preserved, rarely translated, and almost never widely taught. In most of Europe, Aristotle still reigned, not just as a thinker, but as the authority. University students in the 13th century weren't encouraged to challenge Aristotle. They were expected to memorize him. Even questioning his ideas could get you accused of heresy. Truth wasn't something you discovered, it was something you inherited. And yet these early cracks mattered, because ideas, even suppressed ones, don't just vanish. They circulate, they leak into books, letters, debates, they lie dormant, waiting. By the time the Renaissance rolled in, Europe began rediscovering ancient texts, many preserved in Arabic translations, and with them the seeds of a new mindset. A mindset that didn't worship knowledge, but tested it. This was the turning point. The old guard still believed, if a statement was logical and elegant, then it had to be true. But the new thinkers were starting to whisper something heretical. What if it feels right, but it's actually wrong? That single question, doubt in the face of elegance, was the fuse. The explosion was coming. In the next part, we meet the man who lit the match, and built the first physics lab using ramps, marbles, and water clocks. His name was Galileo, and he turned falling objects into falling empires. Galileo and the invention of experiment. By the late 1500s, the world was shifting. Old ideas were cracking, but the real fracture, the one that split science from philosophy, would come from a man with a telescope and a ramp, Galileo Galilei. If Aristotle was the storyteller of the natural world, Galileo was its first fact-checker. And he didn't do it with complex machines or vast laboratories. He did it with balls, inclined planes, and a stubborn refusal to trust intuition. Let's start with a legend. You've probably heard it. Galileo climbs the Leaning Tower of Pisa, drops 2 balls of different weights and proves in front of a crowd that they hit the ground at the same time. Is it true? Historians debate it. But the physics is correct. For centuries, Aristotle's idea had reigned. Heavier objects fall faster. And to be fair, in air, that kind of looks true. Drop a rock and a feather, and you see the result. But Galileo didn't just look. He measured. He set up inclined planes, long ramps tilted at shallow angles, to slow down the motion of falling objects. Instead of hitting the ground in a fraction of a second, he could now observe them in slow motion. He used water clocks to track time, literally measuring how much water dripped out of a container. While the object rolled, it was crude, it was brilliant, and it changed physics forever. Here's what he discovered. When you let a ball roll down a ramp, the distance it travels is proportional to the square of the time it's been moving. In modern terms, we'd write this as di time mort pumps a time t. Distance equals 1/2 acceleration times time squared. But Galileo wasn't thinking in formulas. He was thinking in patterns, and he saw it. Motion followed rules, not purpose, not nature, rules. This was radical, because it said, nature is mathematical, not symbolic, not mythic, not divine, just predictable. You didn't have to be a philosopher. You just had to measure carefully and trust the result. And for Galileo, this wasn't just about rolling balls. He turned his gaze upward, to the heavens themselves. In 1609, he heard about a Dutch invention, the telescope. He built his own, made it better, and aimed it at the moon. What he saw shocked Europe. Craters, mountains, imperfections. The moon wasn't a perfect celestial sphere. It was rough, damaged, Earth-like. Then he pointed it at Jupiter and discovered 4 tiny moons orbiting the planet. This was huge, because it violated everything Aristotle and Ptolemy had taught. Not everything orbited Earth. Not everything was perfect and unchanging. The sky was not sacred. It was a place full of motion, chaos, structure, and evidence. But Galileo didn't stop at observing. He argued, he published, he wrote in Italian, not Latin, so regular people could understand. And that made him dangerous, because he wasn't just discovering new truths. He was unseating old ones. In 1632, Galileo published dialogue concerning the two chief world systems, a debate between a Copernican and a defender of Aristotle. It didn't end well. The Pope, once an admirer, felt mocked. Galileo was summoned before the Inquisition, tried, forced to recant, placed under house arrest. He lived the rest of his life in silence. But the silence was too late. The damage was done. Galileo had proven something more important than any law of motion, that the universe doesn't care what feels true, it only cares what is true. He turned physics from a branch of philosophy into a method: observe, measure, doubt, repeat. That was the revolution. In the next part, we meet the thinkers who followed in his wake and pushed math to the center of nature itself. Kepler, Descartes, and the rise of the mechanical universe. Kepler, Descartes, and the rise of the mechanical universe. Galileo cracked the door open. But he didn't walk through it alone. After him came a wave of thinkers, each more daring, more precise, more mathematical. They didn't just want to challenge Aristotle, they wanted to replace him. And they weren't interested in poetic purpose or divine order. They wanted something colder, more exact, a universe that ran like a machine. Let's start with a man who stared at the sky and trusted the data more than the dogma. Johannes Kepler. Kepler wasn't trying to dismantle centuries of astronomy. He just wanted to understand how planets move. For over 1,000 years, people believed planets moved in perfect circles. Because of course they did. Circles were divine, the perfect shape. And the heavens were supposed to be flawless. But Kepler had a problem. The numbers didn't agree. He had access to the best data on the planets ever recorded. Painstaking observations from the Danish astronomer Tycho Brahe. And no matter how hard Kepler tried, he couldn't make Mars fit a circular path. He tried everything: nested circles, tiny adjustments, epicycles. Nothing worked. Until finally, he stopped trying to force nature into his expectations and let nature tell the truth. Mars wasn't moving in a circle. It was moving in an ellipse, a squashed circle, with the sun slightly off-center. That single insight was enough to rewrite the heavens. Kepler didn't stop there. He discovered 3 laws that describe planetary motion. And don't worry, we'll speak them, not recite formulas. First, planets move in ellipses, not circles, with the sun at one focus. Second, planets sweep out equal areas in equal times, which means they move faster when they're closer to the sun and slower when they're farther away. Third, the time a planet takes to orbit the sun is related, mathematically, to its distance from the sun. You don't need to memorize any of that. What matters is this: Kepler used math to describe nature, not to control it, not to philosophize about it, but to listen to it more precisely. That was new. Meanwhile, in France, another mind was building something even bolder: René Descartes. Descartes believed the universe was a vast, interconnected machine. Everything, from the motion of planets to the beating of your heart, was part of one giant system of cause and effect. To Descartes, motion didn't need purpose. It just needed rules. Push something, and it moves. Remove the push, and it keeps going. Sound familiar? It's close to what we now call inertia. The idea that objects in motion stay in motion unless something interferes. But Descartes went further. He imagined all of reality as matter in motion. Tiny particles swirling in a cosmic whirlpool, bumping into each other, transferring momentum, shaping the world. It was an early form of what we now call mechanistic philosophy, the universe as clockwork. Now let's pause here, because this shift matters. Before Kepler and Descartes, people believed that to understand the world, you had to ask what things meant. Why does fire rise? What is the nature of heaviness? What is the purpose of motion? But now, the question had changed. Instead of why does it move, they were asking, how does it move? That single word swap from why to how is what separates ancient thought from modern science. But here's the irony. Neither Kepler nor Descartes fully understood why their models worked. They described the patterns, they built frameworks. But they didn't yet have the unifying force behind it all. They could see that the planets moved, but they didn't know what caused the motion. That final missing piece. The one that would turn math into mechanics, and mechanics into a theory of everything, was still waiting, and it would arrive in the middle of a plague. But even with all this progress, the elliptical orbits, the swirling particles, the shift from why to how, something was still missing. They could describe the motion of the planets, but they couldn't yet explain the force behind it. What was holding the moon in its path? What made an apple fall? And what did that have to do with Jupiter? No one had connected the dots. Not yet. Until a man, isolated during a plague, sat down in the countryside and quietly rewrote the laws of the universe. Newton's universe, forces, laws, and the death of mysticism. In 1665, the Great Plague swept through England. Cambridge University closed its doors. Students were sent home. One of them, a quiet, awkward, intensely curious young man, returned to his family's farmhouse in the countryside. His name was Isaac Newton. He was 22 years old, and in less than 2 years, working alone, he would invent an entire new physics. No formal lab, no grants, just paper, ink, and time. One of the stories we love to tell is the apple. Newton sees an apple fall. He wonders, why does it fall down? Not sideways. What's pulling it? That question wasn't new. But Newton did something no one else had. He asked whether the same force pulling the apple to the Earth might also be pulling the moon toward the Earth, just at a greater distance. Think about that. Before Newton, no one had connected Earth's gravity to the motion of the heavens. One was seen as mundane, the other, divine. But Newton didn't care about that division. To him, it was all one problem. What makes things move? To answer that, he needed a new kind of math. Existing geometry couldn't handle things that changed constantly. Falling objects, curved paths, or the pull of gravity across space. So Newton invented a tool to handle continuous change. Today we call it calculus. It let him describe acceleration, not just as a concept, but as something that could be measured and predicted at every instant. He now had the language he needed to write the laws of motion. And these laws didn't just describe movement, they described cause and effect. Let's walk through them. The first law sounds simple, but it shattered old thinking. An object will stay at rest or keep moving in a straight line, unless something forces it to change. That means motion doesn't need a constant push. You don't have to keep kicking a ball to make it move. If you removed all friction and air resistance, it would just keep going forever. This was the death of Aristotle's physics, which claimed motion needed a mover. Now, motion was natural. Stopping was the thing that needed explanation. The second law told us how motion changes. The more force you apply to an object, the faster it accelerates. But the more mass it has, the harder it is to move. In other words, an object's acceleration depends on both the force you apply and its resistance to change, its inertia. This idea made it possible to calculate how a rocket launches, how a car crashes, or how planets orbit. It's the law behind every bridge, elevator, and spacecraft ever built. The third law is the one everyone remembers. For every action, there is an equal and opposite reaction. Push on a wall, and it pushes back. Fire a bullet, and the gun recoils. A rocket lifts off, not by pushing against air, but by pushing against its own exhaust. These three laws became the foundation of classical physics. But Newton wasn't finished. He turned to gravity, the mystery that had haunted science for millennia. What pulls things to Earth? What holds the moon in orbit? What keeps the planets from flying off into space? Newton proposed something astonishing. Gravity is a force that exists between any two masses, not just on Earth but everywhere. The same invisible force pulling the apple to the ground also pulls the moon toward Earth, and the Earth toward the sun, and the sun toward other stars. Gravity wasn't special. It was universal, and he even showed how to calculate it. He realized that gravity gets weaker with distance, but never disappears. It pulls in proportion to mass, and in inverse proportion to the square of the distance between objects. You don't need the exact words, just understand this. For the first time in human history, we had a set of rules that could describe everything from falling objects to planetary motion in the same system. The sky and the Earth were no longer separate realms. They were part of the same machine. Newton published all of this in his book Philosophiae Naturalis Principia Mathematica, often shortened to Principia. It wasn't easy to read. Even other scientists struggled with it. But its impact was undeniable. It marked the moment physics stopped being philosophy and became predictive, testable, and mathematical. Of course, Newton didn't explain everything. He couldn't say what gravity was, only how it behaved. He gave us the tools to calculate the force, but not its origin. Still, what he did was enough to dominate science for the next 300 years. And for a while, it seemed like we had the full picture. But that picture, neat as it seemed, wouldn't survive forever, because the next generation of thinkers would start asking terrifying new questions. What is time? Is space absolute? What if light always moves at the same speed, no matter what? And one quiet patent clerk in Switzerland was about to rip Newton's universe apart. Aftershock: How Newton Created Predictability and the Illusion of Certainty. After Newton, the world changed. Not just the scientific world, the entire worldview. For the first time in human history, it seemed like everything, from a bouncing ball to the orbit of Saturn, could be described with mathematical precision. No more need for divine explanations. No more guessing, no more purpose baked into nature. We didn't just understand motion, we could predict it. And prediction is power. This ushered in what we now call the Age of Enlightenment. Thinkers, engineers, artists, philosophers, they all started seeing the universe not as a story told by gods, but as a perfect machine. Like a watch, ticking along with absolute reliability. You wind it up, set the gears in motion, and everything plays out exactly as it should. This was the age of confidence, of certainty, of control. And the heart of it all was Newton. A French mathematician named Pierre-Simon Laplace took Newton's ideas and pushed them even further. He imagined a mind, an intelligence vast enough to know the position and velocity of every particle in the universe. If you could know that, Laplace said, you could predict the entire future, every collision, every heartbeat, every thought. To him, the universe wasn't just orderly, it was inevitable. Cause leads to effect, no exceptions. No mystery. You are not choosing. You are playing out a script, written at the birth of the universe. This idea came to be known as determinism, and for a while, it became the default setting of Western science. Physics wasn't about uncovering surprises. It was about refining the clockwork. You didn't ask, why does it do that? You asked, how precisely can we calculate it? And the answers were astonishing. We built steam engines, mapped the solar system, designed bridges and cathedrals with unshakable precision. Even chaos began to feel like a technical problem, just a matter of too many variables, not actual unpredictability. But there was something unsettling about this picture. If the universe is a machine, then what are you? A gear, a programmed actor? Do your thoughts mean anything? If they were guaranteed to happen, from the moment the first atom moved, determinism gave us power. But it took something else away: mystery, freedom, wonder. Still, for over 2 centuries, no one could argue with the results. Newton's laws worked, the math worked, and as far as anyone could tell, they would always work. But there were cracks beneath the surface. Little anomalies. Things Newton's framework couldn't fully explain, like the orbit of Mercury, which deviated ever so slightly from what the equations predicted, or the nature of light, which seemed to behave like a wave in some experiments, but like a particle in others. Or the troubling fact that gravity appeared to act instantly, with no time delay, even across vast distances. It was almost perfect, but not quite. And then came the really uncomfortable question. What if space and time aren't what we think they are? In the early 20th century, a young patent clerk in Switzerland was quietly thinking about trains, clocks, and beams of light. He didn't have a lab, he didn't have funding, but he had something else: an obsession with consistency. Why does light always move at the same speed, no matter how fast you're moving? What happens to time if you travel near the speed of light? What does gravity feel like? Not from the outside, but from inside a falling elevator. These questions would lead him to a new theory. one that would not destroy Newton's physics, but reveal its limits. And suddenly, the universe wasn't a predictable machine anymore. Time could bend, space could warp, and certainty was no longer certain. So that's where our story heads next. Clockwork cracks. What Newton couldn't explain. For over 200 years, Newton's laws seemed unshakable. They explained falling apples, cannonballs, tides, planets, even comets, obeyed his equations. It felt like the universe had finally surrendered its secrets. But then, cracks began to appear. Tiny ones, easy to ignore, but persistent. And when a theory is truly perfect, even a small crack means something big is wrong. The first hint came from Mercury, the closest planet to the Sun. When astronomers tracked Mercury's orbit, they noticed it didn't quite behave. It looped around the Sun, just as Newton predicted. But the point of closest approach shifted slightly every time, like the orbit was wobbling, drifting forward, bit by bit. This wasn't a fluke. They measured it again and again, and Newton's laws got it almost right, but not exactly. At first they blamed other planets. Maybe their gravity was nudging Mercury off course. But when every factor was accounted for, something was still off. Newton's equations were close, but not perfect. Meanwhile, another mystery was brewing, this time not in the sky, but in the lab. Physicists were trying to understand light. What is it? How fast does it go? And does it follow the same rules as everything else? If you're in a car moving towards someone who throws a baseball, you experience the ball moving faster than if you were standing still. That's just common sense. Speeds add up, but light didn't care about common sense. In 1887, two scientists, Michelson and Morley, set out to measure how the motion of Earth through space affected the speed of light. They built a sophisticated setup with mirrors, lasers, and interference patterns. They expected to see tiny differences in light speed, depending on the direction it was moving. What they found was nothing, no difference at all. The speed of light seemed to be constant, no matter how fast you were moving, and that was deeply, deeply weird. Think about this. If you're driving toward a flashlight, you'd expect the beam to hit you faster, right? But according to the experiment, you get hit by the light at the same speed, as if you were standing still. That's not just strange, it breaks the rules of Newtonian motion. Something was wrong, either with the speed of light, or with our entire understanding of space and time. Now here's where the story takes a sharp turn. Because while all of this was happening, Mercury misbehaving, light refusing to cooperate, a young patent clerk in Switzerland was quietly thinking about trains, clocks, and moving observers. His name was Albert Einstein. He wasn't a professor. He wasn't working in a lab. He was reviewing inventions for the Swiss Patent Office, and in his spare time, he was asking questions that no one else dared to ask. What if the problem wasn't the light? What if the problem was time? See, everyone had always assumed that time was universal, that there was a single ticking clock for the entire cosmos, that now on Earth is the same as now on Jupiter or Pluto or in another galaxy. But Einstein began to suspect that this idea so basic, so obvious, was completely wrong. If light speed stays the same for everyone, no matter how fast they're moving, then something else has to give. Maybe time isn't absolute. Maybe space isn't fixed. Maybe what we call reality isn't what we think it is. It's hard to overstate how radical this was. Newton had given us a universe of certainty, where everything could be predicted, calculated, and mapped. Einstein was about to burn that universe down, but not with chaos, with a new kind of logic, one where the rules are still precise but much, much stranger. In 1905, he published a paper titled On the Electrodynamics of Moving Bodies. No fanfare, no press conference. Just a 26-year-old explaining that space and time are not separate things, but one thing. And when you move fast enough, time slows down, distances shrink, events change order. The world hadn't seen anything like it before, and it all began because a few tiny cracks in Newton's clockwork refused to go away. Speed of light, the law that refused to break. Light should have been easy. We'd measured it. We knew how fast it went, nearly 300,000 kilometers per second. That's about 7 times around the Earth in a single second. But there was a problem. It didn't behave like anything else. Everything else in the universe follows this rule. If you move towards something that's moving, it hits you faster. If you move away, it hits you slower. Simple. A car coming at you at 60 kilometers per hour hits harder if you're running toward it. If you're running away, it's less violent. That's how motion works. It's intuitive, it's Newtonian. But light breaks this. Imagine this. You're standing still. Someone shines a flashlight toward you. The beam hits you at the speed of light, exactly what you'd expect. Now imagine you're running toward the flashlight, say, at half the speed of light. You'd expect the light to hit you faster, right? But it doesn't. You still measure it, hitting you at the exact same speed, 300,000 kilometers per second. Now try running away from the flashlight. Surely the light should hit you more slowly. Nope. Still 300,000 kilometers per second. No matter how fast you go, no matter what direction you move. Light doesn't care. It always hits you at the same speed. This is profoundly weird, because it means that our usual way of thinking about motion, adding speeds together, subtracting them apart, completely fails for light. This fact had been known for a while. As we mentioned earlier, the Michelson-Morley experiment tried to detect the ether, a mysterious medium scientists believed light had to travel through. Just like sound needs air, they thought light needed something to wiggle through. This invisible substance called the ether. They figured that as Earth moved through space, the speed of light would change slightly, depending on whether it was moving with or against the ether wind. So they built one of the most precise experiments ever designed. 2 beams of light, traveling in different directions, reflected by mirrors, creating interference patterns. Any change in the speed of light would show up as a shift in those patterns, but the shift never came. Light speed stayed constant, every time, in every direction. This result was terrifying. It didn't just mean the ether didn't exist. It meant the entire foundation of how motion was supposed to work was broken. And physicists didn't like that. Some tried to patch Newton's equations. Others ignored the problem entirely. But Einstein leaned into it. He accepted the weirdness fully. He said, if the speed of light is always the same, then time and space must not be. Let that sink in. To preserve the constancy of light, we had to give up something deeper. The idea that time ticks the same for everyone. Here's a way to imagine it. Picture 2 people holding identical clocks. One stays on Earth. The other climbs into a spaceship and takes off at an incredible speed. From the Earth's point of view, the astronaut's clock runs slower. From the astronaut's point of view, Earth's clock is the one that slows down. Who's right? They both are, because there is no single, universal clock. Time is not fixed. It bends, it stretches, it dilates, depending on your speed. This is what the constant speed of light forces us to accept. Let's try another analogy. Think of reality as a stage. On Newton's stage, the set never changes. The floor is flat, the clock is ticking evenly. The actors move around, but the structure stays the same. On Einstein's stage, the moment someone moves fast, the floor tilts, the distances shrink. The clocks tick differently. The stage itself becomes dynamic, relative to your motion. Why does this matter? Because it means that the world you experience depends on how you're moving through it. The faster you move, the more time bends, the more space contracts. And all of this, every strange effect, flows from a single, untouchable rule. The speed of light is always the same, no matter what. This is the cornerstone of special relativity, and it breaks our oldest assumptions. Einstein didn't bend the rules to fit intuition. He bent intuition to fit the rules. And from that one choice, a whole new reality opened up. Next, we step into that reality, where time slows, length shrinks, and simultaneity turns out to be an illusion. Special relativity. Time slows, length shrinks, reality breaks. Let's say you have a twin. You stay on Earth. They hop into a spaceship and take off at near the speed of light. They're gone for what feels like 2 years, by your clock. But when they return, you've aged, maybe 10 years, and they've only aged 2. You're both shocked. And yet, neither of you made a mistake. Time actually passed differently for each of you. This isn't a theory. This is a measurable, real, experimentally confirmed fact. It's called time dilation, and it's one of the strangest but most important consequences of Einstein's special relativity. Here's why it happens. Remember, the speed of light is always the same, no matter how fast you're moving. To make that work, something else has to flex, and that something is time. Let's use a thought experiment. Imagine a spaceship with a light bouncing between two mirrors, one on the ceiling, one on the floor. Every time the light hits a mirror, it ticks like a clock. From the point of view of someone inside the ship, the light goes straight up and down. The time between bounces is constant. Now imagine someone outside the ship watching it fly by. To them, the light isn't just going up and down, it's tracing a diagonal path. Because the whole ship is moving sideways, the light travels a longer distance for each tick. But light speed can't change. So to keep the speed of light constant, the clock must tick more slowly. In other words, moving clocks run slow. From the perspective of someone at rest, this is not a malfunction. This is not an illusion. This is what time does when you move fast enough. And we've actually measured it. In the upper atmosphere, there are particles called muons, tiny, short-lived cousins of electrons. They're created when cosmic rays hit the Earth's atmosphere. Muons decay in microseconds. They shouldn't live long enough to reach the surface. But we detect them on the ground, because from our perspective, their clocks are running slower as they fall toward us at near light speed. Time dilation is real, and it shows up in our everyday world, but that's only half the story. Because time isn't the only thing that bends, length does too. This is called length contraction. The faster you go, the more space compresses, in the direction of your motion. Let's go back to our spaceship, to the traveler inside. The distance to the next star is, say, 4 light-years away. If they're moving at nearly the speed of light, you'd expect it to take 4 years, right? But from their perspective, space itself is shrinking. The distance shortens. They reach the star faster, because the universe has contracted around them. Meanwhile, back on Earth, you still measure the full distance, and you see their clock ticking slowly. Again, no one is wrong. This isn't trickery. This isn't distortion, it's relativity. Each observer experiences a different version of reality, and both are equally valid. But here's where things get truly strange. It's not just that time slows or space shrinks. It's that what's real depends on how you're moving. There is no single absolute timeline. There is no universal now. You're not just moving through space, you're moving through space-time. And how much space or time you experience depends on your speed and your frame of reference. That's the core of special relativity. Special, not because it's rare, but because it only applies in situations without gravity, where everything is moving in straight lines, not curving through gravitational fields. Einstein would tackle gravity later, but even in this simplified version of reality, everything we thought we knew about motion and time was already collapsing. In one stroke, Einstein replaced Newton's idea of time as a single steady tick with something far more flexible and far more unsettling. Time and space are not fixed backgrounds. They are part of the story. They respond to motion. They shape your experience. And they are not the same for everyone. Reality, it turns out, depends on how you move through it. But we're not done yet. Because if time isn't the same for everyone, then neither is the order of events. What you call now might not exist for someone else. Next, we'll look at how even simultaneity, the idea of two things happening at the same time, falls apart under the weight of Einstein's logic. And once that's gone, there's no going back. Simultaneity is a lie. Why now doesn't exist. Imagine lightning strikes a train track in 2 places, one at the front of the train and one at the back. You're standing on a hill, watching from a distance. Both flashes reach your eyes at the same moment. You say, they happened at the same time. Seems obvious. But now, imagine someone is sitting on a train, moving along those tracks. They're exactly in the middle of the train, between the 2 strikes. As they move forward, they're getting closer to the front strike, and farther from the rear. From their perspective, the flash at the front reaches them before the flash at the back. Same lightning, same event, different conclusions. Who's right? They both are. Because what's simultaneous, what happens at the same time, depends on where you are and how you're moving. This is the part of relativity that breaks the most brains, because we all walk around with the same invisible assumption that now is universal, that there's a single, shared moment in time, stretching across the cosmos like a master clock. One universal present. Einstein proved that's an illusion. There is no such thing as a shared now across space. Once you accept that time is flexible, that it bends and slows depending on motion, then you have to accept that simultaneity isn't real. It's not a flaw in your perception, it's a flaw in Newton's model of time. Let's go back to the train. You and your friend both observe the lightning strikes. You say, they were simultaneous. They say, one happened before the other. And you both have evidence. Your light waves reached you at the same time. Theirs didn't. This isn't about reaction time or optical illusion. This is built into the structure of space-time itself. Einstein showed that once you accept the constancy of the speed of light, you are forced to accept that different observers will disagree about the order of events. That's not optional. It's built into the math and confirmed by countless experiments. But what does this mean in real life? It means that there is no global now, no line that says, this is what's happening in the entire universe at this exact moment. What's happening right now on a planet 10 light-years away? There's no objective answer. It depends on who you are and how you're moving. This sounds absurd because our brains aren't built to think this way. We evolved for local experience, for survival, for what's in front of me right now. The idea of a relative now is so foreign. We instinctively reject it. But the universe doesn't run on intuition. It runs on structure. And in that structure, time is not flat, it's warped, and simultaneity is just an illusion. Here's another way to visualize it. Think of space-time as a massive loaf of bread. Each slice is a moment in time. We imagine ourselves moving forward through the loaf. Each second, a new slice. But in Einstein's universe, there's no single way to slice the loaf. How you cut it, what counts as now, depends on how fast you're moving. Different observers cut different slices. They see different sets of events as happening at the same time. There is no master slice, no master clock, no master present. This idea isn't just philosophical, it has real consequences. It means that if you're moving fast enough, you can influence which events are in your past and which are still in your future. In some frames of reference, two events are simultaneous. In others, one causes the other. In others, the order is reversed. Reality becomes a network of perspectives, not a single, objective timeline. And if that doesn't sound like science fiction, you're not paying attention. But this is what happens when you take the speed of light seriously. You don't just change how fast light travels. You change what time is. You change what now means. You change what reality is made of. It's not about clocks. It's not about lasers. It's about something deeper. You are not moving through time. You are moving through space-time. And where you are, and how fast you're going, literally defines the slice of reality you experience. And yet, Einstein still wasn't done. He had one more insight to add. If motion affects time, then gravity must affect time too. And that leads us to his next leap, where he stops treating gravity as a force and starts treating it as a curve in the fabric of reality itself. Mass is just frozen energy. You've seen it everywhere. T-shirts, coffee mugs, tattoos. E equals mc squared. It's probably the most famous equation in history. But ask most people what it actually means, and you'll get a blank stare. So let's slow down. Forget the symbols. Forget the hype. Let's talk about what this equation is really saying, and why it quietly rewrote the very fabric of reality. Here's the basic translation. Mass and energy are the same thing. That's it. That's the entire idea. But like most profound truths, it's deceptively simple, because until Einstein came along, we treated mass and energy like completely separate concepts. Mass was stuff, the weight of a rock, the bulk of your body. Energy was motion, heat, light, something's had, not something they were. But Einstein saw through that illusion. He realized that mass and energy aren't just related. They are two forms of the same thing. One is frozen, the other is free. Let's break it down. The E stands for energy, the total energy stored in an object. The IMC is mass, how much matter the object contains. And c is the speed of light, a huge number multiplied by itself. Why the speed of light? Because it's the conversion rate. Just like you convert dollars to yen or meters to feet, you convert mass to energy using the speed of light squared. That number is enormous, which means even a tiny bit of mass can become an absolutely huge amount of energy. And that's not just a theoretical curiosity. Let's take a real-life example, the sun. Every second, the sun fuses hydrogen atoms into helium. But when it does, the resulting helium weighs less than the hydrogen that made it. Where did the missing mass go? It was turned into energy, light, heat, radiation. Everything that warms your face on a sunny day was once mass. In fact, the sun converts about 4 million tons of matter into energy every second, and it has been doing that for 4.6 billion years. So when you look at the sun, you're not just seeing light, you're seeing mass being unlocked, mass transforming into energy at unimaginable scale. Now, flip the process. Can we turn energy into mass? The answer is yes. We've done it in particle accelerators. We slam particles together at near light speed, and the sheer energy of the collision creates new particles with real, measurable mass. Energy becoming matter, the reverse of what the sun does. This isn't philosophy, it's physics. And it's happening every day in labs around the world. But let's go darker for a second. Because this idea that mass can release massive energy also led to something else. The atomic bomb, when scientists split the nucleus of an atom in a process called fission. The total mass of the pieces is slightly less than the mass of the original atom. That missing mass is released as energy, and remember, just a tiny amount of mass, multiplied by the speed of light squared, produces an unbelievable explosion. The bomb dropped on Hiroshima converted less than a gram of mass into energy. 1 gram, the weight of a paperclip, was enough to destroy a city. That's how much power is hidden inside mass. Now let's make this personal. You're made of mass. A lot of it. That means you are also made of stored energy. Not metaphorically, literally. If you could somehow convert the mass of your body entirely into energy, you would release more power than every bomb ever detonated in human history, combined. Don't worry, that's not going to happen. But the point is, you are not just stuff. You are potential energy, condensed into a stable structure. So when Einstein wrote E equals mc squared, he wasn't just making a clever equation. He was revealing something elemental. That mass is not fundamental. It's a form of energy. It's trapped motion. It's energy held in place by structure and bonds. This unlocked a new era of physics, from nuclear power to fusion energy to high-energy particle physics. But it also changed how we think about reality, because it means that everything around you, every chair, every planet, every atom, is not stuff in the traditional sense. It's energy in disguise, and you're part of that story. You're not just alive, you're radiant. But energy and mass are just the beginning. Einstein's final breakthrough would come when he realized that gravity itself wasn't a force pulling you down, but a bending of space-time around mass and energy. And once you see gravity this way, everything changes again. General relativity. Gravity isn't a force, it's a curve. For most of human history, gravity felt simple. Drop something, it falls. Jump, you come back down. Planets orbit the sun, the moon pulls the tides. And thanks to Newton, we had an equation that worked brilliantly. Gravity was an invisible force that pulled masses together. The bigger the mass, the stronger the pull. The closer you are, the stronger the effect. Clean, predictive, elegant. But there was a problem. Einstein didn't buy it. He started with a question so simple, it sounds like a child's curiosity. What would it feel like to fall? Not metaphorically, literally. If you were in an elevator and the cable snapped, what would happen in that instant before you hit the ground? You'd float. You'd feel weightless. For a brief moment, it would feel like gravity had disappeared. Einstein realized something profound. When you're in free fall, you don't feel gravity, not because it's gone, but because you and everything around you are being pulled equally. No resistance, no pressure, no tension. It's indistinguishable from being in deep space. This became the seed of Einstein's greatest idea. Gravity isn't a force pulling things down. It's the shape of space-time, curving around mass and energy. Let's break that down. Imagine space and time as a stretchy fabric. Something like a trampoline or a bedsheet, stretched tight. Now place a heavy ball in the center. What happens? The fabric sinks. It curves around the ball. Now roll a marble across the sheet. If the sheet were flat, the marble would move in a straight line. But now it bends around the ball. No one pushed it. There's no force between the marble and the ball. It's simply following the curve of the fabric. This is Einstein's version of gravity. Mass, like the Earth, the Sun, or even you, bends the space-time around it. Other objects don't feel a pull. They're just following the curves in that fabric. And when something curves through time as well as space, its experience of motion, acceleration, and even time itself changes. This is why clocks tick slower near massive bodies. It's not just a gravitational effect. It's the warping of time. Time isn't separate from space. Together, they form a single entity, space-time. And gravity is just what space-time looks like when it's bent. You might be thinking, okay, but is this just a fancy metaphor? Not at all. We've measured it. Let's take something mundane. GPS. Your phone talks to satellites. Those satellites carry atomic clocks, which keep incredibly precise time. But here's the thing. Clocks in orbit tick faster than clocks on Earth. Why? Because they're farther from Earth's mass. Space and time are less curved up there, so time literally passes more quickly. If engineers didn't correct for this, your GPS would drift by kilometers every day. Einstein's equations aren't just for black holes. They're embedded in your Uber ride. And speaking of black holes, they're the ultimate test of this idea. When a star collapses, its mass gets crushed into a tiny point. The curve in space-time becomes so steep, not even light can escape. This isn't gravity pulling light down. It's space-time pinching inward, so sharply, that every possible path bends back inward. From the outside, time slows near the edge of a black hole. From the inside, well, no one really knows. But again, this isn't a force in the traditional sense. It's geometry. It's curvature. It's the shape of the stage we're standing on. Here's another way to picture it. On a mountain, a ball rolls downhill. Not because the Earth pulls it, but because that's the shape of the land beneath it. In Einstein's universe, mass creates hills and valleys in space-time. Planets roll along those curves. Light bends around them. Gravity doesn't act. It shapes. And once you see it this way, you realize Newton wasn't wrong. He was just looking at the shadow. Einstein's general relativity gave us a universe where space and time aren't neutral backgrounds. They're active players. They bend, they ripple, they evolve. And those ripples, we've detected them. When two black holes collided over 1 billion light-years away, they sent waves through space-time itself. Waves we caught here on Earth in 2015. Not sound, not light, gravitational waves. Real proof that space itself can tremble. This was Einstein's final masterpiece. He took the most ordinary experience, gravity, and revealed it as a cosmic illusion, a shadow cast by deeper geometry. And yet, even he couldn't have imagined just how far these curves would reach. Because in the final section, we go deeper into what his theory predicts: black holes, gravitational lensing, time near stars, and the discovery that the universe itself is expanding, stretching and bending in ways no one saw coming. The warped universe, black holes, gravitational time dilation, and the end of straight lines. We used to think of space as empty, a vacuum, a background, silent, passive, neutral. But by the time Einstein was done with it, space was no longer flat, time was no longer steady, and gravity was no longer a force. The universe had become something else entirely. A living fabric that could bend, stretch, and ripple. Let's start with one of the strangest predictions of general relativity. One that sounds like science fiction, but is now scientific fact. Time moves more slowly in strong gravity. This isn't poetry. It's not metaphor. It's measurable. If you take two perfectly synchronized atomic clocks and leave one on Earth while flying the other on a jet, they'll go out of sync. The one that experienced weaker gravity, up in the sky, will tick faster. Even a small difference in altitude, a mountain versus sea level, changes the flow of time. Gravity, it turns out, doesn't just hold you down, it slows you down. This effect is called gravitational time dilation, and it's not just a lab curiosity. It shows up in some of the most extreme environments in the universe, like the edge of a black hole. Black holes aren't holes, they're collapsed stars. Objects with so much mass packed into so little space that they bend spacetime inward like a funnel. Imagine stretching a rubber sheet with a heavy bowling ball. Now imagine piling on more and more weight, until the sheet stretches so far it forms a bottomless pit. That's what a black hole does to space. And to time. If you could hover near the edge of a black hole, not fall in, just hover, you'd see the outside universe speeding up. Minutes for you would be days, years, or even centuries for everyone else. This isn't just a thought experiment. It's the exact effect visualized in Interstellar. When the characters visit a planet near a massive black hole, 1 hour there equals 7 years on Earth. The science advisor for that film, a Nobel Prize-winning physicist. The math checks out. In real physics, the edge of a black hole, the point of no return, is called the event horizon. Cross it, and nothing can escape. Not a rocket, not a signal, not even light. From the outside, it looks like time stops at the event horizon. A falling object appears to freeze, forever hovering at the edge. From the inside, we don't know, because nothing ever comes back to tell us. And yet, despite all this drama, the warping of space isn't limited to black holes. It happens everywhere. Even starlight can be bent by gravity. This is called gravitational lensing. Imagine space is a transparent jelly. When light passes through curved regions near massive stars or galaxies, its path bends. And from Earth, that bending can make a single galaxy appear in multiple places at once. It can stretch or magnify distant objects, allowing us to see things billions of light years away that would otherwise be invisible. We've taken real images of this. Cosmic mirages created by the gravity of invisible objects. The universe is no longer a stage we stand on. It's a player in the story. It shapes what we see, how we move, and even how we experience time. Now here's the twist. Even space itself, the emptiness between things, isn't fixed. In the early 20th century, Einstein thought the universe was static. He even added a term to his equations to keep it from expanding. But then came observations from Edwin Hubble. He discovered that galaxies are moving away from us. Not just drifting, but accelerating apart. Space itself was stretching. This wasn't galaxies flying through empty void. This was void being created between galaxies. Imagine drawing dots on a balloon and blowing it up. The dots don't move across the surface. The surface itself expands, and they move apart. That's what the universe is doing. And the rate of expansion, it's increasing. We don't know why. We call it dark energy. But that's really just a placeholder, for we have no idea what's causing this. The point is, even straight lines, once the cornerstone of geometry and physics, don't really exist anymore. A beam of light doesn't travel in a straight line. It follows the curve of space. And space curves everywhere. So where does that leave us? In just a few decades, Einstein took us from a world of absolute space and ticking clocks to a universe made of rippling spacetime, where gravity is geometry, where time is personal, and where the universe itself is stretching without end. Reality is no longer a stage, it's a shape. And you, right now, are sitting in a local pocket of curved spacetime, on a spinning rock, in a galaxy being flung outward by the silent expansion of everything. With that, we close the chapter, from Newton's falling apples to Einstein's falling elevators, from force to fabric, from certainty to curvature. We've reached the edge of classical physics. And what comes next will take us into a world even stranger, where particles are waves, cats are alive and dead, and reality itself refuses to be observed without changing. The quantum crack. Why classical physics broke at small scales. At the end of the 19th century, most physicists thought their work was basically done. Sure, there were a few unresolved problems, but nothing major. Newton had explained motion. Maxwell had unified electricity, magnetism, and light. Thermodynamics had mapped the laws of heat and energy. All that was left, many believed, were a few minor details, just some tidying up. The universe, it seemed, was a grand mechanical system. Everything could be predicted, explained, and measured if you just looked closely enough. But then something started to break, and not slowly, violently. It began with light, and with a strange problem no one could quite explain. Physicists were studying black-body radiation. The glow objects emit when heated. You've seen this, a stovetop burner turning red, metal glowing orange before it melts. Scientists built formulas to describe how much energy this glowing light should carry at different wavelengths. The predictions matched well at long wavelengths, like infrared and red light. But at short wavelengths, like ultraviolet, the math went off the rails. According to classical physics, a hot object should emit infinite energy in ultraviolet light. That's nonsense, of course. It became known as the ultraviolet catastrophe. Something was clearly wrong, not with the experiment, but with the theory. In 1900, a German physicist named Max Planck made a desperate move. He proposed something radical. Maybe energy doesn't flow smoothly. Maybe it comes in packets, little indivisible chunks he called quanta. It wasn't what he wanted to say. He thought it was just a trick, a mathematical fix. But the fix worked. It matched the experimental results perfectly. Planck had no idea what he'd just done, but history does. He had lit the fuse of quantum physics. Soon after, another mystery arrived, this time from the photoelectric effect. Here's the setup. Shine light onto a metal surface, and electrons are ejected. Easy enough. But the details didn't make sense. According to classical wave theory, a brighter light, more intense, should eject more energetic electrons. But that's not what happened. What mattered wasn't intensity, but frequency. A dim beam of blue light could knock electrons loose, but even the brightest red light did nothing. Why? Because something was off in the very nature of light. Enter Albert Einstein. In 1905, he took Planck's idea of energy quanta and applied it to light itself. He proposed that light wasn't just a wave, it was made of particles. Tiny packets of energy called photons. And the energy of each photon depended not on brightness, but on frequency, its color. This explained the photoelectric effect beautifully. But it came at a cost. It shattered the classical idea that light was only a wave. Now it behaved like both wave and particle, and nobody was comfortable with that. Then came electrons. People assumed they were tiny particles, like miniature billiard balls. But in certain experiments, electrons behaved like waves too. They interfered, they diffracted. They didn't just hit a spot, they spread. Particles were acting like waves. Waves were acting like particles. The basic categories of reality were melting. And the old physics simply couldn't keep up. One physicist after another began to realize the classical view of nature, with fixed trajectories, continuous energies, and predictable motion, no longer applied to the microscopic world. A new kind of theory was needed. One that allowed for uncertainty. One that let observation change outcomes. One that replaced certainty with probability. And what emerged from that chaos was quantum mechanics. But this wasn't just a change in math, it was a change in philosophy. In reality itself, because the closer scientists looked at the fabric of the universe, the more it seemed to shift, shimmer, and evade any firm answer. What is a particle? What is a measurement? Is the world always there, or does it snap into focus only when we look? These weren't just academic questions. They were forced upon us by experiment. The universe, it turned out, was less like a machine and more like a game of dice. A game where the act of watching might change the outcome, and where the rules only made sense once you gave up trying to imagine what's really happening. The cracks were now a canyon. Classical physics wasn't broken in just one place. It had collapsed at its foundations. And what rose from that rubble was a framework so strange, so deeply counterintuitive, it still puzzles us today. In the next part, we'll walk straight into the heart of that weirdness. A simple experiment that destroys everything you think you know about reality. And it all begins with two slits and a beam of light. Particles or waves. The double-slit experiment destroys reality. If there's one experiment that breaks reality clean in half, This is it. Simple in setup, devastating in meaning. It's called the double-slit experiment. And it starts with a question. What is light? Is it a wave, like ripples on a pond? Or a particle, like tiny bullets? Historically, this debate went back and forth. Newton thought it was particles. Huygens said waves. Then Maxwell's equations made the wave view dominant, until Einstein showed that light could behave like particles too, photons. So which is it? The double-slit experiment said, both, and neither, and more. Here's how it works. Take a laser and aim it at a barrier with two narrow slits cut in it. On the other side of the barrier is a screen that records where the light hits. If light is just made of particles, we'd expect to see two bright bands behind the slits, the way two streams of pebbles would hit a wall. But that's not what we see. Instead, we get an interference pattern, a series of bright and dark stripes, as if the light waves are overlapping, reinforcing and cancelling each other. In other words, light goes through both slits, interferes with itself, and lands in many places at once. That's wave behavior. Okay, fine. Maybe light is a wave. But now comes the twist. Let's turn the laser down. Way down. So low that we're only sending one photon at a time. Now there's no wavefront, no group of photons to interfere with each other. Just single particles, one by one. And yet, as we keep firing individual photons, the interference pattern still appears. A single photon seems to go through both slits, interfere with itself, and then land in a place consistent with a wave-like probability. This makes no sense in classical terms. How can one particle take two paths? What is it interfering with? It's not behaving like a solid thing. It's behaving like a possibility cloud. But now comes the part that breaks people. Let's try to measure which slit the photon goes through. Just put a tiny detector at each slit. Shouldn't be a big deal. We're not stopping the photon, just watching it. But the moment we try to observe which slit it passes through, the interference pattern disappears. Suddenly, photons behave like particles again. Two simple bands, no interference, no wave-like mystery. The act of observing changes the result. Let that sink in. Just looking, just trying to gain information, collapses the wave-like behavior into a definite path. The universe, it seems, decides what it's doing, only when you ask. Before that, it's not a particle. It's not a wave. It's not anything we can describe in classical terms. It exists as a range of possibilities. Only when observed does it choose a reality. This isn't a fluke. We've done this experiment with electrons too. Electrons, the things that make up atoms. Solid matter, same result. Fire one electron at a time through the double slits. And over time, they form an interference pattern, as if each one is going through both slits. Try to observe which slit it chooses. Interference vanishes. Again. The universe behaves differently when you watch. Now you might think, okay, so our detectors are just interfering with the system. That's fair. But physicists have designed incredibly subtle variations of this experiment, including something called the delayed choice quantum eraser. In it, we can wait until after a photon passes through the slits to decide whether to measure it as a wave or a particle, and the pattern we see on the screen, interference or no interference, seems to depend on a decision made after the photon was already detected, which raises a question no one really likes. Is the future affecting the past? Or is reality not decided until we observe it, even retroactively? So what does this all mean? It means that, at the quantum level, reality isn't just unknown before measurement, it's undefined. There is no thing traveling from source to screen. There's only a set of probabilities, a wave function describing all possible outcomes. And the moment we look, that wave function collapses. The possibilities vanish. One reality appears. This isn't just philosophical, it's baked into the math. Quantum mechanics doesn't describe objects. It describes outcomes and the chances of those outcomes happening. The wave function isn't a physical wave, it's a probability wave, a mathematical tool for predicting what you'll see when you check, which leads to the unsettling implication. Until you observe it, the universe doesn't commit. In the next section, we'll explore the principle that defines that fuzziness, the rule that says, even with the best tools in the world, you'll never know everything about a particle. not because you're clumsy, but because the particle itself doesn't have definite properties until you interact with it. Heisenberg's uncertainty. You can't know everything at once. Imagine you're watching a car speed down the highway. If you're standing at a fixed point with a good radar gun, you can measure exactly how fast it's going. And if you snap a photo, you can know exactly where it is. In classical physics, you can always do both, know the exact position and velocity of an object. That's what Newton assumed, and it's how the world seems to work on everyday scales. But at the quantum level, this certainty vanishes. You can't know both where a particle is and how fast it's going at the same time with perfect precision. That's not a technological limitation. It's a law of nature. This is Heisenberg's uncertainty principle. And it's not just about measurement, it's about what can be real. Here's the idea, simplified. Let's say you want to measure the position of an electron. To do that, you need to bounce some kind of light, a photon off it, but that photon has energy. And when it hits the electron, it knocks it off course. The more precisely you try to pinpoint the electron's location, the more you disturb its momentum. And vice versa, if you try to measure its momentum very accurately, you have to sacrifice clarity on position. The act of measuring one quantity introduces uncertainty into the other, but Heisenberg went further. He didn't just say, our tools mess things up. He said, the particle itself does not have both an exact position and an exact momentum at the same time. Those properties aren't real in the classical sense, until they are measured, and even then, only one is sharply defined. So how uncertain are we talking? There's a mathematical limit to how precisely you can know both. The more accurate your knowledge of a particle's position, the less accurate your knowledge of its momentum, and vice versa. You can shrink the uncertainty on one, but only by inflating the other. It's not just that you're missing information, there is no additional information to find. Let's try a real-world analogy. Imagine trying to take a clear picture of a spinning fan blade. If the shutter speed is too slow, you'll get a blur. You don't know exactly where the blade is. But you can see how fast it's spinning. If you use a very fast shutter to freeze the motion, you capture a sharp position, but you've lost all information about how it's moving. That's not a perfect analogy, but it gets at the trade-off. In quantum physics, this isn't about camera settings, it's the fundamental structure of reality. And it's not just position and momentum, there are other quantum pairs like this. Energy and time, for example. You can know the exact energy of a system, but only if you measure it over a long period. If you only watch it for a very short time, the energy becomes fuzzy. This isn't just academic. It explains why virtual particles can appear from nothing, as long as they disappear quickly enough, that their existence doesn't violate energy conservation in a measurable way. It's also key to understanding quantum tunneling, radioactive decay, and why particles in a box can never be perfectly still. But what does this mean for reality? It means the quantum world isn't made of hard-edged things, with properties waiting to be revealed. It's made of probability distributions, blurry clouds of what might be true. Until something interacts and collapses those possibilities into a result. This might sound like everything's just fuzzy and chaotic, but weirdly, it's not. The uncertainty principle is precise, predictable. It defines strict boundaries, not chaos, but rules about what can exist. You can't build an electron with zero motion in a pinpoint location. You can't freeze a photon in place and know where it's going. These combinations of properties simply don't exist in nature, and this has a hidden consequence. There is a limit to how much we can ever know. Not because of bad tools, not because of bad data, but because the universe does not allow full transparency. It holds some cards close to the chest. Not out of malice, but by design. That's unsettling to many scientists. Because for centuries, science was about uncovering truth. Heisenberg showed that sometimes, truth doesn't exist until you ask, and once you do, you collapse the options. You make one version of reality real, and lose the others forever. So now we know that particles don't have fixed properties, that observing them defines them, and that even the best questions have no perfect answers. But how far does this go? What if a particle here could somehow know what happens to a particle over there? Instantly, no matter how far apart they are? What if nature isn't local? In the next part, we dive into the phenomenon Einstein hated most, but which experiment has confirmed again and again. It's called entanglement, and it might be the weirdest thing in the universe. Schrödinger's cat, when probability becomes flesh. In 1935, Erwin Schrödinger was frustrated. Quantum mechanics had exploded into physics like wildfire. It was powerful, precise. It could predict atomic behavior with unmatched accuracy, but it was also absurd. And no one seemed bothered by that. So Schrödinger did what physicists sometimes do when the math gets too weird. He told a story, a parable, a trap, a thought experiment, designed not to explain quantum mechanics, but to mock it. Here's how it goes. Imagine a sealed box. Inside the box, there's a cat, alive and well. A small vial of poison, a radioactive atom, a Geiger counter, and a hammer. The setup is simple. If the atom decays, a completely random quantum event, the Geiger counter detects it. That triggers a mechanism that releases the hammer, which shatters the vial, releasing poison. And the cat dies. If the atom doesn't decay, nothing happens. The cat lives. Now here's the twist. According to quantum theory, until you open the box, the radioactive atom is in a superposition of both decayed and not decayed. And because the atom's state determines the cat's fate, the cat is also in a superposition. Not dead, not alive, but both, simultaneously, until you observe it. Only when you open the box does the wave function collapse, and the universe commits to a single outcome. Schrödinger didn't propose this to be clever. He was pointing at something horrifying, because if you follow quantum logic, it's not just tiny particles that can be in multiple states at once. It's anything entangled with them, even cats, even conscious beings. That means superposition isn't just microscopic, it might be universal. And that was exactly his point. If this theory is really true, then reality, as we know it, is broken. Now let's step back. What is superposition, really? It's the idea that at the quantum level, a particle doesn't have a single definite state. An electron isn't just here or there. It's in a combination of all the places it could be. A photon isn't polarized horizontally or vertically. It's in a superposition of both. These are not hidden variables. They're not things we don't know yet. They are literally not determined. It's like asking a coin mid-flip, whether it's heads or tails, and being told, it's neither, it's both, and neither, and more, only when it lands, when you check. Does the answer solidify? So the question is, when does a superposition end? Does it require a conscious observer, just any interaction with a larger system? Or is the whole idea just a placeholder for something deeper? Physicists have debated this for nearly a century. Some say the act of measurement collapses the wave function. Others say, no, the wave function never collapses. We just become part of the entangled system. And each version carries its own strange implications. In one view, reality is probabilistic. In another, every possibility actually happens, in a branching multiverse of outcomes. Schrödinger hated both options. That's why he gave us the cat. To show that the problem wasn't just academic. If superposition is real, then there are moments, infinite moments, when the universe is suspended between truths. When the line between fact and possibility, between existence and non-existence, isn't just blurred, it doesn't exist yet. Let's bring this back to scale. You're not a cat in a box. You're a person in a world, but the same quantum rules apply. Right now, particles in your brain, in your eyes, in your neurons and synapses, are in states of flux, until decoherence or observation settles them. In practice, this doesn't mean your entire body is in superposition. Macroscopic systems interact with their environments constantly, which tends to force outcomes rapidly, but the underlying principle remains. Reality isn't just there, waiting to be uncovered. It's in formation, moment by moment. And somewhere in the basement of physics, a coin is still flipping, over and over, waiting to be seen. Schrödinger's cat wasn't meant to be solved. It was meant to expose the tension at the heart of quantum theory. And it worked. Because nearly 100 years later, we still don't know exactly what collapses a wave function. Or even if collapse is real, all we know is what the math tells us. The world is built on probabilities, not certainties. and the boundary between the possible and the actual runs right through every act of observation. But here's where it gets even stranger. What if particles separated by galaxies can still affect each other instantaneously? What if the collapse of a wave function here collapses another light years away? That's not science fiction. It's called entanglement. And Einstein hated it, which makes it even better. Quantum entanglement, when two particles become one reality. Let's say you have a pair of gloves, one left, one right. You put each into a box, seal them, and send them to opposite sides of the galaxy. You open the first box. It's the right glove. Instantly, you know the other is left. No need to open it. Simple, right? But that's not quantum entanglement. That's just common sense. The gloves had defined identities the whole time. You just didn't know which was where. Entanglement is different, deeply, disturbingly different. Because in the quantum world, the particles are like glove-like, but their identities aren't decided in advance. They don't have a defined left or right until someone checks. And when you do check one, the other seems to snap into place instantly, no matter how far away it is. As if information traveled faster than light. Or as if the two particles are still part of the same system. Despite being separated by billions of kilometers, this is quantum entanglement. And Einstein despised it. He famously called it spooky action at a distance. Because it violated everything classical physics believed, that objects exist independently. That information cannot travel faster than light. That reality is local. What happens here should not instantly affect what happens there. Entanglement breaks all of that, and it's real. Here's how it works. You take two quantum particles, say electrons, and prepare them in a special way, so their properties become linked. For example, their spins, a kind of intrinsic angular momentum, can be set up so that they are always opposite. If one is up, the other will be down. If one is down, the other is up. But, and this is the key, neither particle has a defined spin until one of them is measured. Until that point, both are in a superposition of spin up and spin down. Only when you measure the first does the other snap into the opposite value, instantly. Even if they're on opposite sides of the universe. Now pause for a second. This isn't about classical uncertainty. It's not that the values are hidden and we're just uncovering them. The mathematics and repeated experiments say that the values do not exist until measurement. This bothered Einstein. He insisted the theory must be incomplete. There had to be some hidden variables, some deeper level of reality, that determined the outcomes in advance. Otherwise, how could the universe allow such instantaneous influence? In 1964, physicist John Bell came up with a way to test it. He derived a set of mathematical inequalities, now called Bell's theorem, that could tell us whether entangled particles were just using hidden variables behind the scenes, or whether something genuinely non-local was happening. The result? Experiment after experiment violated Bell's inequalities, and as technology improved, the loopholes closed. No hidden variables, no classical explanation. Entanglement is real. So what does that mean? It means quantum mechanics is non-local. There is no signal being sent between particles, because there's nothing to send. The particles don't carry individual identities. They are part of a single quantum state, spread across space. Your act of measurement isn't just discovering something. It's participating in a system that extends beyond you. In a very real way. What you do here affects what's real over there. Let's pull this into something human. Imagine you and someone else are playing a game. You're each given a particle from an entangled pair. You go to opposite ends of the Earth. You both choose at random how to measure your particle. When you compare notes later, you find your results are correlated more strongly than any classical system allows. Not just similar, too similar. It's as if reality knew both of your decisions in advance. Even though they were made independently, in different places, with no way to communicate. And that raises disturbing questions. Is there a deeper layer of reality that's non-local? Does information exist outside of space and time? Or does space itself not really exist at the quantum level? Modern quantum field theory goes even further. It suggests that entanglement is the fabric of space itself. That without entanglement, there would be no connectivity, no spacetime at all. In this view, Particles aren't things in space. They are excitations of relationships. Reality, then, isn't made of matter. It's made of correlation. You can't pull the universe apart into isolated pieces. Everything is always part of something larger. And yet, you don't see this in your daily life. Why? Because entanglement doesn't scale easily. The second you try to measure a quantum system, or it interacts with its environment, it decoheres, loses that fragile entanglement. But make no mistake, at the fundamental level, the universe is not made of separate pieces. It's a web, a unity. A strange, vibrating, probability-soaked unity, where what's here and what's there are not as separate as they seem. So far, we've talked about particles. But what if the real foundation of reality isn't particles at all? What if everything, electrons, photons, even atoms, are just temporary ripples in a deeper field? Next, we leave behind the idea of stuff and enter the world of quantum fields. The quantum field. Reality is just ripples in the void. When most people picture particles, they imagine tiny marbles. Little solid objects bouncing around, colliding, forming atoms. Even in quantum physics, it's tempting to hold on to that image. Electrons, photons, neutrons. But the deeper we go, the more that image fails. Because in modern physics, particles aren't the foundation of reality. Fields are. Invisible, continuous, ever-present fields, stretching across all of space. And particles? They're just ripples in those fields. Temporary disturbances, fleeting patterns. Localized excitations that look like stuff, but aren't really stuff at all. Let's take a step back. You've probably heard of the electromagnetic field. It's what creates radio waves, sunlight, magnetism. That field exists everywhere, even in a perfect vacuum. Now imagine that idea, a field, omnipresent, not just for electricity and magnetism, but for everything, for electrons, for quarks, even for the Higgs boson. Every fundamental particle has a corresponding quantum field. So instead of saying, here's an electron field, physics says, there is an electron field. And somewhere in it, there's a ripple, a little bump of energy. And that is what we call an electron. In this view, reality is not made of things. It's made of interacting vibrations in invisible fields. Think of the surface of a calm pond. Now drop a pebble. A ripple spreads out. That ripple isn't a new thing added to the pond. It's just a change in the water's state. That's what a particle is. A change in a field, concentrated enough to behave like an object. This is the heart of quantum field theory, QFT, one of the most successful scientific frameworks ever created. QFT doesn't describe particles moving through space. It describes fields shifting, interacting, colliding in bursts of energy that we detect as events. And because quantum mechanics still applies, the energy in these fields doesn't change continuously. It jumps in discrete packets, quanta. That's why it's quantum field theory. Every click on a detector, every spark in a cloud chamber, is not a solid object arriving. It's a field interaction, crossing a threshold. So what makes one kind of particle different from another? It's which field is vibrating and how. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. A quark is a ripple in the quark field. Each field has different properties. Mass, charge, spin, interaction rules. But the structure is the same. Everything is a wave. Not a wave on water, not even a wave in space. A wave in abstract mathematical space, a field of potential values at every point in the universe. Now this might sound like philosophy, but it's not. This is how the standard model of particle physics works. The most accurate, precise framework in science. We've used QFT to predict particle behavior to 12 decimal places. That's like measuring the width of the United States to the accuracy of a human hair. We used it to predict the Higgs boson, decades before we found it. We use it to run particle colliders, build electronics, design lasers, MRI machines, and GPS satellites. It's not just an idea. It's the blueprint of the invisible. But there's something eerie about this view. It means that even in a perfect vacuum, where there's nothing, the fields are still there. And they're never completely still. They fluctuate. This is called vacuum energy. the idea that the emptiest space still has jittery energy from quantum fields. This energy is real. We've measured its effects, most famously in the Casimir effect, where two uncharged metal plates in a vacuum attract each other because of differences in field fluctuations between them. In other words, empty space pulls. Nothingness is not nothing. So where are we now? We've gone from particles to wave functions, from wave functions to fields, and from fields to a view of the universe where the real entities are mathematical distributions of potential, waiting to ripple into something observable. It's like saying, reality is music, and particles are the notes, but the instrument, the strings beneath it all, are the fields. And what we call matter, that's just a particularly stable melody. This changes how we think about identity. If every electron is a ripple in the same field, then every electron in the universe is fundamentally the same, not just similar, identical, indistinguishable. There is no this electron and that one. There is only the electron field and its temporary excitations. This isn't poetry. This is testable physics. But there's one field we haven't mentioned yet, and it's the one that gives mass to everything. It's called the Higgs field, and it's not just a background player. Without it, all particles would move at the speed of light. There'd be no atoms, no stars, no us. In the final part of this chapter, we'll explain how mass itself emerges from interaction, how the Higgs field slows the universe down just enough to let complexity form. The Higgs field, why the universe has weight. You're sitting still, maybe in a chair. Gravity holds you down. Your muscles press against the weight of your own body. It's such a basic experience having mass that we forget to ask a deeper question. Why do you have mass at all? Why do particles resist acceleration? Why do atoms have weight? Why isn't everything just pure energy zipping around at the speed of light? This isn't a small mystery, because in the early universe, before one moment of symmetry broke, nothing had mass. Everything was massless, like photons, particles of light. And then, something changed. A field turned on. It filled the universe like an invisible ocean. And particles moving through that ocean began to drag, to slow down, to acquire what we now call mass. That field is the Higgs field. Let's unpack this slowly. In quantum field theory, every particle is a ripple in a corresponding field. We covered that. But here's the problem. When you build a theory of particle interactions, there's nothing in the math that automatically gives particles mass. And that's a big issue. Because mass is what allows structures to form. Without it, electrons wouldn't bind to atoms. Atoms wouldn't cling together into matter. Everything would fly apart at the speed of light. For decades, this gap in the standard model was a gaping hole. Then in the 1960s, Peter Higgs, along with several other physicists, proposed an elegant solution. What if space itself had a background field, like a cosmic molasses, and some particles interacted with it more than others? The more a particle interacted with this field, the harder it was to push, the more mass it seemed to have. Particles that didn't interact with it at all, like the photon, would remain massless, zipping around at light speed. This was more than a metaphor. It became the Higgs mechanism. To visualize it, imagine a crowded room. Let's say you're a celebrity, and you try to walk across. People surround you, slow you down, try to talk to you. You can still move, but you feel heavier, like you're dragging social mass. Now imagine someone else, a nobody, walks through the same room. No one notices. They glide through untouched. That's the difference between a massive particle and a massless one. The room is the Higgs field. Your interaction with the crowd is what gives you mass. This idea was bold, but it had consequences. If the Higgs field is real, then just like any other field, it should have a particle, a ripple, the Higgs boson. But it was elusive. For decades, scientists searched for it. Nothing. It became the last missing piece of the standard model. The God particle, some called it, much to the annoyance of physicists. Then, finally, in 2012 at CERN's Large Hadron Collider, after decades and billions of dollars, we found it, a blip, a bump in the data, a confirmation that the Higgs field is not just theory. It's part of our universe. But let's take a step back from the celebration and look at what this really means. It means the vacuum isn't empty. Even in the absence of particles, the Higgs field is there, everywhere, always. It doesn't switch on and off. It's part of the structure of space itself. You are swimming in it. Your body is built from particles that owe their very identity to how they interact with it. Without the Higgs field, you'd be weightless, not in the floaty, fun way, but in the terrifying, disintegrating way. Nothing could hold together. No stars, no chemistry, no life. But there's something even more sobering. Most of your mass of any object's mass doesn't actually come from the Higgs field. It comes from the energy of quantum interactions inside particles like protons and neutrons. The Higgs gives mass to the quarks and electrons, but the gluon fields binding quarks together generate most of what we experience as mass. This ties back to Einstein's insight. Mass is energy. Even the weight of the world is mostly energy, trapped and dancing inside tiny fields. So why care about all this? Because it changes how we see ourselves. We often think of matter as primary, of having mass as being real. But mass isn't a thing. It's a response, a consequence of interaction. Reality isn't solid. It's fluid, relational, dynamic. You're not a fixed object. You're a storm of fields, interacting, resisting, vibrating, made heavy only because space lets you be. And if the Higgs field had a different value, by just a fraction, you wouldn't exist. And that closes chapter 3. We began with the collapse of certainty, and we've ended with the fabric of identity. Particles don't exist until observed. Their properties can't all be known. They can be entangled across space, emerge from fields, and take on mass only by moving through a silent, omnipresent medium. So what is real? According to quantum physics, that's still an open question. What is entropy? From disorder to information theory. Let's start with something deceptively simple. You walk into a room and see a deck of cards, neatly arranged by suit. Ace through king. 4 perfect stacks. You knock the table. The cards scatter. That feels normal. But imagine the opposite. A chaotic pile of cards suddenly jumps into 4 perfect suits, snapping into order with no one touching them. You'd be disturbed. That's not how the world works. But why not? The laws of motion, the math of particles, none of them technically forbid it. So what's really going on? That's where entropy comes in. At its core, entropy is about counting possibilities. It measures how many ways a system can be arranged, without changing what it looks like overall. In the case of the card deck, there's only one way to be perfectly ordered. But there are trillions of ways to be messy, so randomness tends to win. This isn't a law of motion. It's a law of likelihood, and it governs everything from melting ice to the fate of the entire universe. The idea of entropy first emerged in the 1800s. When engineers were trying to improve steam engines, they noticed something strange. No matter how efficient the machine, some energy was always lost as unusable heat. This wasn't mechanical failure, it was a deep physical limit. So they defined a quantity to measure it: entropy, a kind of energy price tag for disorder. And the second law of thermodynamics was born. In any isolated system, entropy tends to increase. But what does disorder actually mean? It's not about mess in the everyday sense. It's about how much you don't know. Think of a gas in a box. If all the molecules are clustered in one corner, you can describe that situation precisely. But if they're flying around randomly, you can't describe exactly where each one is. You can only give probabilities. That's higher entropy, more uncertainty, more informational ignorance. And here's the bridge to something profound. In the 20th century, scientists like Claude Shannon noticed that this wasn't just about heat or molecules, it was about information. In fact, Shannon borrowed the word entropy to describe the uncertainty in a message. If a sentence is full of repetition, you can compress it. If it's full of surprise and randomness, you can't. More surprise, more entropy, more information, but also more unpredictability. Entropy became not just a property of matter, but of meaning itself. This is where physics meets philosophy. Entropy tells us how the universe evolves, but it also tells us something about our knowledge of that evolution. It's a bridge between the material world and our perception of it. When entropy increases, you lose precision, You lose reversibility, and you lose the ability to rewind. You can know less about a system's past once it becomes more entropic. It's like watching cream mix into coffee. You see the end result, but not the exact path that got it there. Entropy isn't just about physical disorder. It's about the loss of memory in the system itself. So next time you spill a deck of cards, or watch smoke drift into the air, or forget what you had for lunch last Tuesday, you're witnessing entropy in action, not as some vague force of chaos, but as the mathematical heartbeat of a universe that favors probability over perfection. It's not evil, it's not broken, it's just the way the numbers work. And those numbers, the invisible statistics behind every irreversible moment, are what give time its direction. The second law of thermodynamics. Why heat flows one way. You pour hot coffee into a cold mug. A few minutes later, it's warm, but not scalding. What happened? The heat spread out. It didn't stay put. It didn't get hotter. It equalized. And crucially, you've never seen the reverse. No mug has ever, on its own, made cold coffee hot again. Why not? After all, the microscopic laws that govern atoms and molecules are time-symmetric. They work just as well forwards as backwards. If we could track every particle, every vibration, nothing in Newton's or Schrödinger's equations says heat can't flow from cold to hot. And yet it never does. Why? Because of the second law of thermodynamics. It says, in any isolated system, the total entropy, the measure of disorder, always increases or stays the same, never decreases. But why is this so important? Because it's the only fundamental law in physics that introduces a direction to time. Gravity doesn't care about direction. Neither does electromagnetism, but entropy, it only grows. And that's why you remember yesterday, but not tomorrow. Why smoke drifts but doesn't undrift. Why life has a past and not just a collection of events. Let's break it down through a real-world example. Imagine a box divided into two halves by a wall. One side is full of gas molecules, the other is a vacuum. Remove the wall. The gas spreads out instantly, evenly. Now, technically, there's a tiny probability that all the gas molecules could bounce around and eventually gather themselves back into one half. But the number of possible arrangements where they're evenly spread is astronomically higher than the number of ways they're neatly packed. So while reverse motion isn't forbidden, it's so improbable that we'll never see it happen. That's what the second law describes. Not impossibility, but overwhelming likelihood. Here's an analogy that helps. Picture a pristine library, every book shelved in perfect order. Then, imagine a small earthquake shakes the building. Books fall, papers scatter. Now ask, what are the odds that same shaking would reshelve them again, by title and author? The physics doesn't prevent it, but statistically, it's a cosmic joke. The second law is that joke written in the language of particles. It's also why heat is so special. Heat is just disorganized energy, energy in motion, but with no preferred direction. And because particles tend to share that energy through collisions, it always flows from more to less, from hot to cold. You'll never see an ice cube in tea get colder while the tea gets hotter. Not because it can't happen, but because it's so staggeringly improbable that the universe simply doesn't bother. This principle shows up everywhere. In biology, why you need to eat to offset internal entropy. In engineering, why no machine is ever 100% efficient. In cosmology, why stars die and energy degrades. Computers, why deleting data creates heat. Even thinking, even remembering, burns energy, increases entropy. The second law is not a suggestion. It's a deep statistical truth. But here's the real twist. The second law doesn't just explain why some things happen. It explains why anything happens at all. Because if entropy never increased, there'd be no flow of energy, no gradients, no work, no life. In a perfectly balanced world, nothing moves, nothing changes. Entropy is the engine that makes motion meaningful. So the next time you watch steam rise, or ice melt, or your phone battery drain, you're not just seeing decay. You're seeing the deep statistical logic of a universe, in motion, and behind that motion, the invisible hand of the second law, pointing one way only. Irreversibility. Why you can't unshatter a teacup. Picture this. You're standing in your kitchen, holding your favorite porcelain teacup. It slips. Gravity does what it does. The cup shatters into 20 sharp, glittering pieces on the floor. Now hit rewind. Mentally, not literally. Can you imagine those shards pulling together, flying upward, reassembling into the exact teacup, warm and whole in your hand? You can imagine it. But you'll never see it. Why? Because while physics allows it in theory, the universe refuses in practice. This is the heart of irreversibility. It's not about physical laws. Those are reversible. It's about statistics, information, and the sheer imbalance of possibilities. Let's unpack that. At the microscopic level, the level of atoms and molecules, the equations of motion don't care which way time flows. Whether a particle moves left or right, forward or back in time, the math works the same. But when you scale that up to objects, to systems, to life, things change. The number of ways for a cup to be broken vastly outweighs the number of ways it can be whole. One precise configuration gives you a perfect teacup. Millions of combinations give you a scattered mess. That's entropy again, the measure of disorder, or more precisely, the number of microscopic ways to achieve a macroscopic outcome. So when the cup breaks, entropy rises, and the second law kicks in. There's no going back. Not because it's impossible, but because it's overwhelmingly unlikely. Here's a real-world analogy. Think of a jigsaw puzzle, complete and beautiful on the table. Now throw it into the air. You've introduced disorder. Sure, in theory, one of those tosses could result in it landing perfectly formed again. But you'd be waiting longer than the age of the universe to see it. Irreversibility isn't about rules being broken. It's about the asymmetry of probability. The world is free to run backwards, but it almost never will. This has profound consequences for how we experience reality. We don't just observe time moving forward. We experience causes followed by effects. Memories pointing one way, decisions made, not unmade. Why do we remember yesterday, but not tomorrow? Because yesterday's lower entropy state left records. Photographs, brain activity, broken teacups. Tomorrow hasn't happened yet, not because it's missing, but because it hasn't left traces. Entropy increases, and in doing so, it erases the path back. That's why your cream won't unmix from your coffee. Why smoke doesn't go back into the candle. Why lives move forward. The arrow of time emerges from this irreversible erosion of order. In fact, every act of destruction is really a transformation, from specific structure to generic randomness. And the more specific something is, the more fragile, detailed, or ordered, the easier it is to break, and the harder it is to restore. A shattered sculpture, a corrupted file, a reputation. They all follow the same statistical logic. And that's the deep link between physics and human life. Entropy doesn't just govern molecules. It governs memories, trauma, decay, and the impossibility of perfect repair. But here's something to sit with. Irreversibility creates meaning. If nothing ever changed, if every broken thing could be unbroken without consequence, then experience would be cheap. There'd be no stakes, no history, no story. Entropy makes the present precious, because it won't come again. And this brings us naturally to the bigger scale. If teacups can't unshatter, what does that say about stars, galaxies, black holes? If entropy always increases, if structure always decays, then what is happening to the entire universe? That's where we're headed next. We've explored entropy in your kitchen, in your thoughts, in your coffee. Now we'll step out to the cosmic canvas to see what happens when the universe itself follows the same irreversible script. Entropy in the universe, stars, black holes, and heat death. The stars in the night sky might look eternal, but they're not. Each one is a furnace of order, holding off entropy. For now, they burn hydrogen into helium, fusing light elements into heavier ones. In doing so, they release light, heat, and radiation, and, more importantly, they increase entropy. This might sound paradoxical. How can stars, the most organized and luminous objects we see, be engines of disorder? But that's exactly what they are. Stars don't fight entropy. they accelerate it. Let's take a step back. The early universe, right after the Big Bang, was hot, dense, and almost perfectly uniform. No galaxies, no stars, just a sea of energy and particles. Surprisingly, this was a low entropy state, because even though it was hot and chaotic, it was simple. There weren't many ways to rearrange it that would look different. It's like having a room full of identical ping-pong balls. Chaotic motion, sure, but no real structure. Over time, gravity amplified tiny differences, pulling matter into clumps. Stars formed, then galaxies, then clusters. Structure emerged, but so did entropy. Why? Because while small pockets of order were created, the total disorder, the overall entropy of the universe, kept rising. You can think of it like this. A star is like a fire in a cold room. It creates local order, a structured ball of burning gas, but only by dumping even more disorder into its surroundings, as light and heat. The second law is never violated. The cost of every pocket of order is paid by increasing entropy elsewhere, and when a star dies, entropy doesn't stop, it spikes. Some stars collapse into white dwarfs. Others explode in supernovae, leaving behind neutron stars or black holes. And black holes, they're the most entropic things we know of. Strangely, the more mass a black hole has, the more entropy it contains. Not because it's chaotic inside, we don't know what's inside, but because of what's lost to the outside. When matter falls in, its information is seemingly erased. Irretrievable. This led physicist Jacob Bekenstein and later Stephen Hawking to realize black holes have entropy and even temperature, which means, according to thermodynamics, they must eventually evaporate. Slowly, yes. Incomprehensibly slowly. But they're not eternal. Entropy wins again. Now stretch this to the far future. As stars burn out and black holes dissolve, the universe trends toward its most probable state. Thermal equilibrium. No stars, no gravity wells. Just a thin, even mist of cold particles, spread so uniformly that nothing can happen. No energy differences to drive reactions, no gradients to do work, no memory, no structure. Just stillness. This is called the heat death of the universe. Not because it's hot, but because all the heat has already been used. Entropy has maxed out. The universe didn't explode. It didn't collapse. It just ran out of surprises. And here's the strange part. This future isn't defined by something breaking. It's defined by everything being finished. The end state of entropy isn't chaos. It's uniformity. A cosmic sameness, so complete. There's no meaningful distinction left. In a way, entropy doesn't destroy structure. It erases differences, but that's what makes now so rare. We live in a universe that hasn't reached equilibrium. Stars still shine, life still stirs. Time still matters. Entropy hasn't won yet, which means we're in a brief window, a cosmic blink, where complexity can exist. You, listening to this right now, are part of that temporary complexity. Entropy is rising, but not done, not yet. The low entropy of the past. Why the universe started in an ordered state. Let's start with a basic question. If everything trends toward disorder, then why was the universe so ordered in the first place? That's not a rhetorical question. It's one of the deepest unsolved mysteries in physics. Entropy increases. We know that. But to increase, it had to start low. And it did. The early universe wasn't just hot and dense. It was extraordinarily uniform. Same temperature everywhere. No stars, no galaxies, no structure. Just a smooth field of energy, like an untouched canvas. To our everyday thinking, that sounds messy. But in the language of entropy, it was astonishingly ordered. Let's use an analogy. Imagine a mountain made of sand, a towering, perfect cone. That's order, a very specific structure. Now kick it. The grains scatter, the shape collapses. That's entropy increasing. But for that increase to be possible, you had to start with something unlikely, a neat pile of sand. In the same way, the universe began with very low gravitational entropy. All the matter was spread out evenly. And that's actually the least probable way matter could be arranged under gravity. Because gravity loves clumps. It pulls things together. If left alone, Mass collapses into stars, planets, black holes. Uniformity is fragile. It takes almost no effort for it to fall apart, and yet, for some reason, our universe started in that highly uniform state. This is not just a technical curiosity. It's the entire reason time flows the way it does. If the early universe had already been in equilibrium, if entropy had already been maxed out, nothing would ever change. No stars, no chemistry, no life, no clocks, no arrow of time. But here's where the mystery deepens. Why was the entropy so low at the beginning? Was it a cosmic coincidence, a special condition imposed by the Big Bang? Or is there some deeper principle at work? We don't know. Some physicists, like Roger Penrose, have proposed that the initial conditions of the universe were subject to incredibly precise constraints, so precise in fact, that the probability of them happening by chance is something like 1 in 10 to the 10 to the 123. That's a number so absurd, you couldn't write it down even if every atom in the universe were a digit. Others suggest that maybe we're just seeing one bubble of a much larger multiverse, and we happen to live in the one that began in an ultra-low entropy state. But those are still speculative ideas. What we do know is this. Low entropy at the start is not explained by the laws of physics we have. The equations of motion, from Newton to Einstein to quantum mechanics, don't tell us where to begin. They only tell us what happens after something has already begun. So the question of the low entropy beginning is like asking, why was the stage so perfectly set before the play began? We don't have a script for that. Yet, ironically, everything we see around us, life, evolution, memory, direction, story, depends on that initial asymmetry, the ability to grow, to age, to remember. It's only possible because the past is different from the future. Entropy increases because it started low. Time moves forward because the conditions behind us were special. The smoothness of the early universe wasn't just a footnote in cosmology. It was the seed of all future complexity. And here's a humbling thought. We may never know why it was like that. The beginning of time may be forever out of reach. A mystery baked into the structure of reality. But mystery is not failure. It's a frontier. And every step we take toward understanding entropy is also a step toward understanding ourselves and why we remember, change, and move forward at all. Statistical mechanics. How randomness makes rules. Imagine you flip a coin once. Heads or tails? 50-50. Now flip it 10 times. Still random, but maybe you get 6 heads, 4 tails. Now flip it 1,000,000 times. Suddenly, you'll find it almost always lands close to 500,000 heads and 500,000 tails. Why? Because randomness, when repeated enough, becomes predictable. That's the paradox at the heart of statistical mechanics. The science of how individual chaos gives rise to universal order. To understand this, let's start with gas. Take a sealed box filled with air. Inside, there are quintillions of molecules, bouncing off the walls, colliding with each other, all flying in different directions at varying speeds. Now ask yourself, how could we possibly know what's going on? We can't track every molecule. That would require more information than atoms in the universe. But here's the trick. We don't need to, because while any single particle is unpredictable, the average behavior of all of them together is extraordinarily stable. That's where temperature, pressure, and volume come from. They aren't about individual particles. They're about the collective effect of all their randomness. It's like crowds at a stadium. No one can predict what one person will do, but we can model how 70,000 people will behave during halftime. They'll move toward exits, form lines, buy snacks. There's structure in the chaos. In the same way, statistical mechanics lets us define precise rules. For systems made of particles we can never individually observe. This shift in thinking was revolutionary. In the 19th century, physicists like James Clerk Maxwell and Ludwig Boltzmann realized that thermodynamics, the science of heat, work, and energy, wasn't about mysterious forces. It was just statistics applied to atoms. Maxwell introduced probability distributions to describe molecular speeds. Boltzmann took it further, linking entropy directly to the number of microstates, the different ways particles could be arranged, while still looking like the same macrostate. He even had this engraved on his tombstone, sich K log W, where S is entropy, K is Boltzmann's constant. WELI is the number of microscopic configurations consistent with a given state. This simple-looking equation tells us that entropy increases because there are more ways for things to be disordered than ordered. It's not magic. It's just math, counting the possible arrangements. Now here's the deeper implication. The laws of thermodynamics, things we treat as fundamental, are really emergent. They come from large numbers, from the fact that when you have enough particles, the unlikely stuff disappears. Sure, a box of air could spontaneously move all to one side, but the number of arrangements where it's evenly distributed is so vast in comparisons that it's what we always see: the arrow of time, the flow of heat, the mixing of cream into coffee. They're all just statistical trends. They're not dictated by an absolute commandment from nature, but by the law of large numbers. And this applies far beyond physics. Think about traffic patterns, crowd dynamics, stock markets, even language use. Whenever you have many individual actors, random behavior starts to form statistical regularities. Statistical mechanics isn't just about gas in a box. It's a philosophy of how order emerges from ignorance. It shows us that we don't need certainty to have structure. We don't need to know everything. We just need to know enough. And that brings us back to entropy. Why does entropy increase? Because in any system with many particles, the odds overwhelmingly favor states with more micro-configurations, more ways to exist, more paths to get there. It's not fate. It's just that disorder is more probable than order, by numbers so large they defy imagination. So next time someone says, randomness means chaos, rememberness means chaos. Sometimes randomness is the only way to get law. The mystery of time's direction. Why entropy defines past and future. Let's say you watch a video of a glass falling off a table and shattering on the floor. Now play it backward. Instantly, you know something's wrong. The shards don't leap up. They don't form a perfect glass. Your brain rejects it as unnatural, almost disturbing. But from a physics standpoint, that backward video is just as valid. The equations work both ways. So why does the forward version feel right, and the reverse feels like science fiction? What gives time its direction? Why do we remember the past but not the future? Why do we age, grow, decay, but never reverse? Why does a cause lead to an effect, and never the other way around? It all comes back to entropy. Let's unpack this. At the microscopic level, Newtonian mechanics, quantum mechanics, even general relativity, none of these theories contain an arrow of time. They're all time symmetric. You can run the math backward or forward. It still works. So where does the irreversibility of life come from? It comes from statistics, from entropy, from the fact that, on a macroscopic scale, there are more ways for things to be messy than tidy. Entropy gives time its one-way street. Here's a simple analogy. Imagine a giant deck of cards, perfectly sorted by suit and rank. Now start shuffling. Each shuffle increases disorder. It's easy to go from order to chaos. But going from chaos to order, that would require an exact sequence of reverse shuffles. In theory, possible. In practice, absurdly improbable. The arrow of time isn't about possibility. It's about probability. Forward is more likely than backward, by such a wide margin. We mistake it for inevitability, and this shapes everything about how we live. Memory, for example, is a record of low-entropy past states stored in our high-entropy present brains. You don't remember the future, because the future hasn't left any physical imprints yet. No burned paper, no cracked cups, no digital photos, no trails for your brain to follow. All memory, at its core, is asymmetry, a leftover of when things were less entropic. That's why you can't uneat food, or unsay words, or unexperience trauma. Because the systems involved, your body, your mind, the room around you, have already moved on. The configuration has changed, the options have narrowed, entropy has increased. And it won't go back. Now think cosmically. The universe started in a low entropy state, smooth, structured, full of gradients. From there, entropy has been rising relentlessly. That increase is what gives us narrative. Not just in stories, but in physics. The past was ordered, the present is messier, the future will be more so. Without that slope, that gradient, you couldn't build a clock, tell a story, or make a decision. There'd be no before and after, just a frozen stasis. And here's the philosophical kicker. The flow of time, this most basic, intimate human experience, might not be fundamental. It may just be an emergent illusion, created by the statistical behavior of particles in a lopsided universe. In a sense, time doesn't move, entropy does. And we, with our brains built to track patterns and remember impressions, ride that wave. We surf the increasing entropy of the universe, confusing the slope for a direction. So next time you glance at a ticking clock, or notice a wrinkle in the mirror, or catch yourself longing for the past, remember, you're not watching time unfold. You're watching possibilities collapse. You're watching the universe climb the entropy ladder, one irreversible step at a time. And somewhere between the cracks, between the past that left traces, and the future that hasn't yet, lives the strange, fragile miracle of now. What is the Standard Model? Overview of quantum building blocks. If you strip everything away, the books on your shelf, the cells in your body, the atoms in those cells, what are you really made of? Not metaphorically, literally. Down to the smallest components, nature allows. Physicists have spent over a century peeling back that onion. And what they've uncovered is strange, elegant, and surprisingly minimal. It's called the Standard Model, and despite its dry-sounding name, it's one of the most successful scientific theories in history. It explains what everything is made of, and how those things interact, except gravity, which we'll get to later. Think of the Standard Model as the periodic table of fundamental reality. But instead of elements like hydrogen and gold, it lists the true ingredients. Particles so small, you've never seen them, but everything you've ever touched is built from them. So what is it? At its core, the Standard Model describes two categories of things. Matter particles, the stuff, force carriers, the glue. Let's start with the stuff. The Standard Model says all matter is made from 12 particles. That's it, 12. These are called fermions, and they come in two families, quarks and leptons. Everything you see around you, stars, rocks, trees, people, is made from just 3 of these. The up quark, down quark, and electron. That's astonishingly efficient. With just those 3, nature assembles atoms, molecules, cells, planets. It's like building the entire universe using only Lego bricks in 3 shapes. Now, how do these particles interact? Through forces, but not the everyday kind you think about. In the quantum world, forces aren't invisible pushes. They're caused by exchanges of particles. For example, when 2 electrons repel each other, it's because they're trading tiny packets of energy called photons, the same particles that make up light. The Standard Model includes 3 fundamental forces. Electromagnetic, carried by photons. Strong nuclear, carried by gluons. Weak nuclear, carried by W and Z bosons. These forces govern everything from chemical bonding to radioactive decay to the stability of atoms. But here's the beauty of it all. Each particle in the Standard Model has a role, and each interaction has a rulebook. Together, they form a kind of cosmic operating system, a set of instructions that determine how particles behave, how they combine, how they decay. And just like software, these rules are incredibly precise. Experiments have tested the Standard Model to 14 decimal places, and it keeps getting the right answer. That's not common in science. That's rare. That's suspiciously perfect, and yet it's not complete. It doesn't include gravity. It can't explain dark matter. It has over a dozen adjustable constants that nobody understands why they're set the way they are. It's more like a brilliant but unfinished masterpiece, something we know works, but clearly isn't the final answer. Still, what it has achieved is profound. The Standard Model has unified forces. It's predicted particles years before we discovered them. It underpins the machines that scan your brain, power your phone, run your GPS. Without it, modern technology and modern understanding would collapse. And here's the real kicker. The universe, in all its richness, emerges from particles that are almost nothing. They have no size, no shape, no internal structure. Many of them pass through your body right now, unnoticed, and yet their patterns of interaction, Build everything you see. That's the standard model. A framework not of things, but of relationships, of rules, of whispers between particles that scale up into the roar of reality. Quarks and leptons, the families of matter. If the standard model is the blueprint for reality, then quarks and leptons are its raw material. These are the fermions, the particles that make up matter itself. They're not the scaffolding. They're not the glue. They're the stuff. And what's striking isn't just what they are, but how few of them there are. Let's start with quarks. There are 6 types known as flavors. Yes, physics has a sense of humor. Their names are up, down, charm, strange, top, bottom. Each comes with an electric charge, and each plays a role in forming larger structures. But only the up and down quarks are needed to build protons and neutrons, which, in turn, make up atomic nuclei. Proton, 2 ups, 1 down. Neutron, 2 downs, 1 up. That's it. Everything from your skin to the sun is built from that basic trio. So why the other 4? We don't know exactly. The charm, strange, top and bottom quarks are heavier, rarer, and decay quickly. They show up in high-energy environments, particle accelerators, early universe conditions, but not in the atoms of your desk lamp. They're like exotic cousins, not part of the daily family, but still written into the genetic code of nature. Now the other family, leptons. Again, 6 types, paired into 3 generations. You've already met the most famous one, the electron. It orbits atoms, conducts electricity, powers everything from lightning to microchips. Next comes the muon, similar to the electron but heavier and unstable. It shows up in cosmic rays and high-energy collisions. Then the tau, even heavier, even shorter-lived. Each of these has a corresponding neutrino. The electron neutrino, muon neutrino, and tau neutrino. Neutrinos are weird. They're incredibly light. They barely interact with anything. Trillions pass through your body every second, like ghosts through walls, and yet they're essential. Without neutrinos, nuclear reactions wouldn't work properly. Stars wouldn't burn the way they do. They're the silent partners in the orchestra of matter, present but almost invisible. So let's step back. 12 particles, 6 quarks, 6 leptons. Arranged into 3 generations, each heavier and more unstable than the last. But only the first generation, up, down, electron, and electron neutrino, makes up the stable matter around us. Why are there 3 generations at all? No one knows. It's like discovering a toolkit with extra strange tools, useful only in rare conditions, but always present. They don't fit neatly into our current understanding, but they exist, and the standard model accounts for them precisely. Here's an analogy. Imagine a set of building blocks in just a few shapes and sizes. You only need 3 or 4 to build everything: furniture, buildings, bridges. And yet, for some reason, the manufacturer also includes extra blocks, massive, unstable ones, that break down if you try to use them. Why? No idea, but they're there. And under extreme conditions, like in particle colliders, or the first seconds after the Big Bang, they come alive. Nature, it seems, is full of prototypes. It doesn't quite throw away. What's truly fascinating is how different quarks and leptons are. Quarks feel the strong nuclear force. They bind together tightly. That's why we never see a quark alone. They're always confined in groups, like prisoners of their own interactions. Leptons, on the other hand, are free agents. Electrons and neutrinos don't bind to each other the same way. They float solo, shaping the world in more subtle ways. Together, quarks and leptons give us structure and behavior. Protons and neutrons from quarks, electrons and neutrinos from leptons. Together, they form atoms, molecules, chemistry, biology, all from just 12 little whispers of reality. And yet, particles don't do anything on their own. They need rules, they need interactions. So next, we'll explore how those particles talk to each other, through forces, fields, and the strange particles that carry them. The fundamental forces, strong, weak, electromagnetic, and the missing one. Imagine a universe made entirely of particles. Quarks, leptons, neutrinos, electrons, just floating in a vast empty void. Would anything happen? Not really. They wouldn't attract, repel, combine, explode, or evolve. They'd just sit there, isolated, silent. Without forces, the universe would be a quiet, pointless soup of particles going nowhere. Forces are what make things happen. They're the verbs in the sentence of the cosmos. In the Standard Model, there are three recognized fundamental forces: electromagnetic, strong nuclear, weak nuclear. These aren't just technical categories. They are the reason anything exists in a coherent, structured form. Let's start with the most familiar, electromagnetic force. This is the force that holds atoms together, makes light, and powers your phone. It acts on anything with electric charge, and its messenger particle is the photon. When two electrons repel each other, they're actually exchanging photons. That might sound strange. How can you throw a photon and repel something? But in quantum field theory, that's how forces work. All interactions happen through the exchange of particles. The electromagnetic force is infinite in range, but it gets weaker with distance, like light from a candle. And crucially, it's incredibly strong compared to gravity. You can pick up a paperclip with a fridge magnet, overpowering the entire mass of the Earth pulling downward. Strong nuclear force. Now this one is different. It only acts at extremely short distances, inside atomic nuclei, but it's the strongest of all. It holds quarks together, inside protons and neutrons. And it holds protons and neutrons together inside nuclei. Without it, atoms would fall apart. Its messenger particles are called gluons. And yes, the name is intentional. Gluons glue quarks together, but they also interact with each other, which makes the math difficult. One bizarre outcome of the strong force is confinement. Quarks can never be isolated. If you try to pull two quarks apart, the force between them increases. Eventually, you pump in so much energy that it creates two new quarks, giving you two quark pairs instead of one. It's like stretching a rubber band until it snaps, and the snap creates new rubber bands. Weird, but that's quantum chromodynamics for you. Weak nuclear force. Despite the name, this one is powerful in its own way. The weak force is responsible for radioactive decay. It's what turns a neutron into a proton, or vice versa, in beta decay. It doesn't hold things together. It changes particles from one type to another. Its messengers are the W and Z bosons. Unusual in that they're massive, which limits the range of the weak force. This force is essential for the fusion reactions that power the sun. Without it, stars wouldn't shine, life wouldn't exist. So yes, it's weak in name, but not in consequence. But wait, where's gravity? You might be wondering, what about gravity? Isn't that a fundamental force? Yes, but here's the twist. It's not part of the Standard Model. Why? Because gravity, as we currently understand it, is described by Einstein's general relativity, which is a classical theory, not a quantum one. The Standard Model is a quantum field theory. It treats forces as arising from particle exchanges. Gravity doesn't fit into that framework. Not yet. Attempts to unify gravity with quantum mechanics, like string theory or loop quantum gravity, are still works in progress. So for now, the Standard Model leaves gravity out. It's like a brilliant recipe that explains nearly everything, except one crucial spice we still can't quite pin down. Together, these three quantum forces govern everything from particle collisions to planetary formation. They determine the shape of atoms, the lifetime of stars, the glow of a light bulb. And they all emerge from invisible exchanges, particles flung back and forth across space, negotiating the very structure of reality. Next, we'll zoom in on those messengers themselves, the bosons that carry forces, including the elusive Higgs. Because understanding the forces is only half the story. To grasp why matter exists the way it does, we need to meet the particles that give it structure and mass. Bosons and force carriers, photons, gluons, WZ, bosons, and the Higgs. So far, we've talked about the particles that make up matter, quarks and leptons, and the forces that make them interact. But there's a missing piece, because in quantum field theory, forces don't just happen, they're carried. In fact, every fundamental force in nature is mediated by a specific kind of particle, a boson. Bosons aren't like electrons or quarks. They don't make up stuff, they make up interactions. They are the messengers that enable the universe to function. When two particles feel a force repelling, attracting, fusing, decaying, what's really happening is that they're exchanging a boson. Think of them like diplomats shuttling back and forth between nations, negotiating how particles should behave. Let's meet the ones we know. Start with the photon, the simplest and most familiar. It carries the electromagnetic force. Every time light hits your eyes, or a microwave heats your food, or a magnet pulls on a nail, you're watching photons at work. Photons are massless and travel at the speed of light because they are light. They're exchanged between charged particles, constantly and invisibly. And even in a vacuum, the electromagnetic field is alive with their presence. Without photons, not only would there be no light, there would be no chemistry, no electricity, no life. Now step into the nucleus, and things get stranger. The strong nuclear force is carried by gluons, appropriately named because they glue quarks together. Inside a proton, gluons are being exchanged so rapidly, with such intensity, that the quarks are effectively trapped. Try to pull them apart, and the force doesn't weaken, it strengthens. At some point, it becomes energetically favorable to produce new quarks out of the vacuum, resulting in two smaller bound systems instead of one. It's like stretching a rope until it snaps, and both ends grow new ropes. That's confinement, one of the weirdest, most powerful features of quantum chromodynamics, the theory governing the strong interaction. Gluons themselves carry the color charge that defines this force, which means they interact with each other, unlike photons, which don't. This self-interaction creates a turbulent, nonlinear field, a storm beneath the surface of every proton. Next are the W and Z bosons, carriers of the weak nuclear force. These are very different from photons and gluons. For one, they're massive, heavier than an iron atom. Because of this mass, the weak force has a very short range, less than the width of a proton. But it plays a critical role in processes like beta decay, where a neutron transforms into a proton by emitting an electron and a neutrino. That process, seemingly trivial, is what allows stars to burn hydrogen into helium. Without it, the sun would be dark. The W and Z bosons are also responsible for turning one type of quark into another. They change identities, something no other force does. In that sense, the weak force is the editor of the Standard Model, capable of rewriting particle types, mid-story. And then there's the Higgs boson. It's not like the others. It doesn't mediate a force in the traditional sense. Instead, it's the visible ripple in the Higgs field, a field that permeates all of space. According to the Standard Model, particles acquire mass through their interaction with this field. Some particles, like the photon, glide through it untouched, remaining massless. Others, like the W and Z, interact strongly and gain mass. It's like moving through a crowded room. If no one notices you, you pass freely. But if everyone wants to talk to you, you slow down. The Higgs field gives particles inertia, resistance to acceleration, which is what mass really is. The discovery of the Higgs boson in 2012 at CERN confirmed a key piece of this picture. It wasn't just the final missing particle in the Standard Model. It was proof that fields, not particles, are the true fabric of reality. So these bosons, massless, massive, fleeting, or stable, don't build matter. They choreograph its motion. They are the reason particles attract, repel, stick together, or fall apart. They're not the actors, but the scriptwriters, whispering instructions across the quantum stage. And yet, among them, one stands apart. Unlike the photon or gluon, this boson doesn't carry a force. It rewrites the rules entirely. Because before we can understand why some particles have mass at all, we have to meet the field that gives mass meaning. Let's talk about the Higgs. Not just the boson, but the invisible field it reveals. The Higgs field. How mass is acquired. Why does anything have mass? Why don't photons, the carriers of light, weigh anything, while W and Z bosons, the force carriers of the weak nuclear force, are some of the heaviest known particles? Why do electrons have a specific tiny mass, and quarks have different, inexplicable ones. This isn't a trivial question. For most of physics history, we simply assumed mass was a fundamental property, like color or charge, something a particle just had, no explanation needed. But the Standard Model doesn't like unexplained assumptions. It demands symmetry, mechanism, structure. It wants to know how and why. And that brings us to the Higgs field. This field, invisible, omnipresent, woven into the fabric of reality, is the reason anything has mass at all. To understand how this works, forget about the Higgs boson for a moment, the particle that made headlines in 2012. That's just the ripple, the wave on the ocean. What really matters is the ocean itself, the Higgs field. Unlike gravity or electromagnetism, which can be turned off in empty space, the Higgs field is always on. It fills the entire universe, even in perfect vacuum. There is no such thing as a place without it. And that's the key. As particles move through the Higgs field, they interact with it, or they don't. The more strongly a particle couples to the Higgs field, the more resistance it feels, like moving through molasses. That resistance manifests to us as mass. It's not that mass is something stuck onto a particle. It's something that emerges from its interaction with this invisible medium. Photons, they glide right through, untouched, no interaction, no mass. When and Z bosons, they slog through it like they're waist-deep in glue and come out heavy. The electron, it couples weakly, just enough to have a small mass, but not enough to weigh it down. This mechanism, called spontaneous symmetry breaking, is one of the most beautiful and subtle ideas in modern physics. Before the Higgs field turned on in the early universe, all particles were massless, all forces were unified. But as the universe cooled, the Higgs field took on a non-zero value everywhere, like a pencil tipping over on its own. Symmetry broke, and suddenly particles behaved differently, depending on how they interacted with the new background field. That tipping point, that transition, was like the universe choosing a specific identity card for every particle. You're heavy, you're light, you're massless. It rewrote the behavior of everything, permanently. Now this is where the Higgs boson, the particle, comes in. Just like photons are ripples in the electromagnetic field, the Higgs boson is a ripple in the Higgs field. It's what you get when you hit the field hard enough, like at CERN's Large Hadron Collider, and make it vibrate. When scientists finally detected the Higgs boson in 2012, it wasn't just about discovering a new particle. It was proof that the Higgs field, this invisible ocean of mass, actually exists. That mass itself comes from something real, not just assumed. And yet, even with this grand discovery, there are unsettling puzzles. Why is the Higgs field's value what it is? Why not a little stronger or weaker? If it were just slightly different, the universe would be unrecognizable. No atoms, no chemistry, no life. This leads physicists into uncomfortable territory. Questions of fine-tuning, vacuum energy, and the possibility of metastable universes. The Higgs field isn't just a mass giver. It might be a ticking time bomb buried in the equations. But before we go there, we still haven't addressed something critical. If the Standard Model is supposed to explain everything, where's gravity? Let's go there next. Why isn't gravity included? General relativity's stubbornness. Gravity is the first force we ever feel. You fall, you walk, you drop your keys. You know it before you can speak. And yet, for all its familiarity, gravity is the one force the Standard Model can't explain. It's not a minor oversight. It's a gaping hole at the center of our understanding. Why? Because gravity refuses to behave like the other forces. Let's unpack what that means. In the Standard Model, the forces are described using quantum field theory. That means every interaction is caused by particles exchanging force carriers, photons, for electromagnetism, gluons for the strong force, W and Z bosons for the weak. These are all quantized fields. Their effects come in discrete packets, and they operate within the framework of quantum mechanics. Gravity, on the other hand, is still described by Einstein's general relativity, a theory from 1915 that treats gravity not as a force, but as a consequence of curved spacetime. According to Einstein, massive objects don't pull, they warp the geometry around them. Planets follow the curves, light bends, time slows. That's gravity. Beautiful, elegant, predictive, but not quantum. And therein lies the problem. General relativity is a classical theory. It doesn't have particles or probabilities. It doesn't fit neatly into the quantum worldview where everything fluctuates and nothing is certain. Attempts to quantize gravity, to create a graviton, the hypothetical force carrier, run into problems. Massive ones. The math blows up. The infinities don't cancel. You can't normalize the equations the way you can in other fields. It's like trying to fit a round planet into a square simulation. No matter how you tweak the parameters, something explodes. This is the heart of the struggle to build a unified theory of everything. There are a few paths forward, but none are complete. String theory suggests that all particles are actually vibrating strings, and gravity arises naturally as one of their modes. It's elegant, higher dimensional, and deeply mathematical. But it's not testable, not yet. Loop quantum gravity takes a different route, trying to quantize spacetime itself, breaking it into discrete units. It's more background independent, but again, it hasn't delivered definitive, observable predictions. In both cases, we're exploring blind alleys and cosmic cathedrals without a map. So gravity remains the odd one out. It's like building a perfect orchestra with strings, brass and percussion, and then realizing the conductor refuses to read the score. There's also a deeper question. Maybe gravity doesn't need to be a force at all. What if it's an emergent property? Not fundamental, but a statistical effect of something deeper? Some physicists have speculated that gravity could arise from entanglement, or from information theory, or even as a kind of thermodynamic entropy gradient. In these models, gravity isn't a fundamental actor. It's a byproduct of the system trying to maximize information or energy flow. Radical, yes. But so was quantum mechanics in 1905. Meanwhile, the practical issue persists. When we try to describe what happens inside a black hole, or at the moment of the Big Bang, we need both quantum mechanics and gravity, and the two refuse to cooperate. It's like trying to merge two brilliant, stubborn geniuses into a single theory and discovering they speak completely different languages. So far, no one's succeeded. That's why physicists still call this the quantum gravity problem. So while the standard model covers almost everything we observe, it cannot describe the force that holds galaxies together, the force that shapes the universe on large scales, the force you feel every time you drop your phone. That's not a small omission. That's a crisis in waiting. And yet, the fact that it works despite this gap is almost as remarkable. Because what we do have is still stunningly predictive, and what we don't have might just lead us to the next revolution in physics. Next, we'll explore the places where that revolution might begin. The cracks in the standard model, where the light starts to shine through. What the model can't explain. Neutrinos, dark matter, and its many gaps. The standard model is one of the most successful theories in science. It has predicted new particles before we discovered them. It has passed every experimental test thrown at it for 50 years. It powers our understanding of atoms, stars, and particle collisions. But if you look closely, it's clear something's missing. More than one something, in fact. Physics doesn't just march forward when theories succeed. It moves when they start to fail, quietly, around the edges. And the standard model has several of those edges. Let's examine a few of the most glaring. Start with neutrinos. The standard model includes them. 3 types, in fact. They're part of the lepton family. They interact weakly. They have no electric charge. They were once thought to be massless. But that's the catch. In 1998, experiments in Japan and Canada found something odd. Neutrinos were oscillating, changing from one type to another as they traveled. That only makes sense if they have mass. And not just any mass that the standard model doesn't account for. This wasn't a rounding error. It was a crack in the foundation. It meant that something fundamental was missing, either a new kind of particle or an entirely new mechanism. And that brings up another point. Why are neutrino masses so tiny compared to every other particle? We still don't know. It's like finding a pebble on a mountaintop and realizing it didn't come from any nearby rock. Now let's talk about dark matter. Everything we see, stars, gas clouds, galaxies, is made of ordinary matter, the kind described by the standard model. But when we measure how galaxies rotate, or how light bends around them, we find something strange. There isn't enough visible mass to explain the gravity. Not even close. In fact, 85% of the matter in the universe is invisible. It doesn't interact with light. It doesn't show up in telescopes, but it has gravity, and a lot of it. This invisible mass is called dark matter, and the Standard Model says nothing about it. None of its particles behave like dark matter should. Not the neutrinos, they're too light and fast. Not the Higgs or the Ballieu or the Z, so there must be more. Physicists have proposed candidates: WIMPs, axions, sterile neutrinos, but so far, no definitive detection. We know it's there, but we don't know what it is. That's not a small oversight. It's 5 times more matter than everything we understand. Imagine writing a recipe that leaves out most of the ingredients and still trying to bake the universe. Then there's dark energy, an even stranger player. In 1998, again that year, astronomers found that the universe's expansion is accelerating. Something is pushing space apart. We call it dark energy. It's not part of the Standard Model either. It makes up nearly 70% of the energy in the universe, which means the Standard Model only explains about 5% of what exists. Let that sink in. It's like saying you understand the ocean because you've studied a teacup of water. There are other gaps too. Why are the masses of the particles what they are? Why 3 generations of fermions and no more? Why does the Higgs field have the strength it does? Why is there more matter than antimatter in the universe? The Standard Model doesn't answer any of these. It just assumes the values, sets them as constants, and moves on. That's not a flaw exactly. Every theory has parameters. But in physics, unexplained parameters are like fingerprints left at a crime scene. They tell you there's a deeper story, one you haven't uncovered yet. So what does this mean? It means the Standard Model is not the end of the road. It's more like a beautifully crafted map, but one that covers only a well-lit island in a much larger, darker sea. That's why physicists are still searching for new particles, new symmetries, new principles. Supersymmetry, extra dimensions, hidden sectors. Maybe the truth is just beyond the next collider. Maybe it's waiting in a dataset we haven't analyzed deeply enough. Or maybe, just maybe, our entire framework needs to change. Because if the Standard Model is this powerful and this incomplete, then the next chapter in physics isn't just an add-on. It might be a whole new way of seeing the universe. The birth of QED. Why quantum mechanics needed a new force theory. The early 20th century didn't just shake physics. It cracked it open. Einstein had shown that space and time weren't fixed. Bohr and Heisenberg revealed that matter behaved probabilistically at small scales. And suddenly, the neat clockwork universe of Newton was gone, replaced by something far weirder. That was quantum mechanics, a theory where particles were waves, where certainty was replaced by probability, and where the act of observation itself changed reality. But there was a problem. Quantum mechanics worked well for isolated particles, a single electron, a hydrogen atom. But what happens when particles interact? What happens when light hits an electron? Or when 2 electrons repel each other? This was where classical physics still hung on. Electromagnetism, described by Maxwell's equations, still treated light as a wave in a field. And it treated charged particles as continuous blobs. That didn't fit with quantum mechanics. Particles weren't continuous. They were discrete. They came in quanta, packets of energy. So if light could act like a particle, a photon, and electrons were quantum objects too, then we needed a way to describe how they talk to each other. And that's what quantum electrodynamics, or QED, set out to do. It would be a quantum theory of the electromagnetic force. But getting there was anything but straightforward. The first breakthrough came in the 1920s and 30s, as physicists tried to merge special relativity with quantum mechanics. That effort produced something remarkable, the Dirac equation, a relativistic wave equation for the electron. It was beautiful. It predicted the electron's spin. And it even predicted something bizarre, the existence of antimatter, a particle identical to the electron, but with the opposite charge. That prediction turned out to be right. The positron was discovered in cosmic rays in 1932. But when physicists tried to go further, to include interactions between electrons and photons, the math broke down. They got infinities. An electron interacting with its own electromagnetic field, for example, would seem to have infinite energy. Physicists were stuck. The theory predicted physical quantities like mass and charge, but gave nonsense answers. The same kind of problem happened again and again. It wasn't just a bug. It looked like the whole system might be fundamentally flawed. Then came the war. During World War II, many physicists were pulled into weapons research, radar, and cryptography. But after the war, in the late 1940s, something changed. A few physicists, including Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, independently found new ways to tame the infinities. They developed a method called renormalization, which we'll get to in more depth later, that allowed the infinite parts of the equations to be absorbed into redefined constants, like the bare mass of the electron. Suddenly, the predictions made sense again. They could now calculate things like the anomalous magnetic moment of the electron, and the results matched experiment with astonishing accuracy. QED wasn't just saved, it was born as a quantum field theory, the first fully successful one. It didn't describe particles as little points bouncing around. It described fields in visible layers that filled space, capable of vibrating, exchanging quanta, and interacting. In this view, particles are just ripples in their respective fields, and interactions happen through the exchange of other ripples, like photons. An electron emits a photon, another absorbs it, and that exchange is the electromagnetic force. No wires, no action at a distance, just ripples talking to ripples. The creation of QED marked a turning point in physics. It was no longer enough to describe what particles did. We had to describe what the fields were doing underneath. And it worked, not just in principle, but with staggering precision. The quantum theory of how light and matter interact was now predictive, testable, and shockingly accurate. But it also introduced ideas that were deeply counterintuitive. Particles that popped into existence and vanished again. Fields that never rested. Interactions that happened through virtual processes. Those ideas would take us into entirely new territory. Next, we'll look at one of the strangest and most important of those ideas, virtual particles. The invisible intermediaries that make all interaction possible. Virtual particles, what they are and how they mediate force. In high school science class, you're usually taught this. Particles interact because of fields, electric fields, magnetic fields, gravitational fields. But that's only part of the story. In the quantum world, forces aren't transmitted by smooth curves or invisible lines. They're mediated by particles, but not in the way you might think. These aren't regular, real particles you can isolate or observe. They're called virtual particles. And they're everywhere, every force you've ever felt, from the light hitting your eyes to the atoms in your body holding together, has involved the silent work of virtual particles. But what exactly are they? And how can something be virtual and still real enough to hold the universe together? Let's begin with a simple interaction, two electrons repelling each other. In classical physics, that's explained by electric fields pushing against each other. In quantum electrodynamics QED, it's much stranger. Each electron is surrounded by a fluctuating electromagnetic field. When they approach, they exchange a virtual photon, and that's what causes the repulsion. It's not that a little sphere flies between them like a tennis ball. Rather, it's a ripple in the quantum field, a borrowed excitation that appears, mediates, and disappears. And here's the key. Virtual particles violate the usual energy rules. Briefly, according to the Heisenberg uncertainty principle, the more precisely we try to define energy, the less precisely we can define time, and vice versa. This means that for very short periods, particles can borrow energy from nowhere, as long as they give it back quickly enough. Virtual particles exist in that loophole. They're not directly observable, but their effects are real. They're allowed to bend the rules. Because the universe allows temporary mischief, as long as the debt is repaid before anyone notices. So why call them particles at all? Because mathematically, they appear in the same equations as real particles. They carry momentum. They carry force. They show up in calculations as intermediate steps, like background actors who never speak but push the plot forward. But they can't be detected directly. Try to observe a virtual particle, and it's no longer virtual. It collapses into something else entirely, or vanishes. They're like scaffolding in a construction site, crucial for the structure, but never part of the final building. This concept doesn't just apply to electromagnetism. In the strong nuclear force, virtual gluons are constantly being exchanged between quarks, creating such intense confinement that quarks can never escape. In the weak force, virtual W and Z bosons can momentarily appear inside atomic nuclei, enabling radioactive decay or the fusion reactions in the Sun. Even gravity, if we ever find a complete quantum theory of it, might be mediated by virtual gravitons, ripples in the spacetime field that only exist momentarily. Every force is, at root, a handshake made through particles that don't really exist, at least not in the classical sense. The implications go deeper. In quantum field theory, empty space isn't really empty. It's seething with fluctuations, particles and antiparticles popping in and out of existence constantly, even in a vacuum. These aren't just theoretical curiosities. They have measurable consequences. For example, the Lamb shift, a tiny difference in energy levels in the hydrogen atom, is caused by interactions with virtual particles in the vacuum. So is the Casimir effect, where two uncharged metal plates placed close together in a vacuum experience a mysterious force pulling them together, a result of vacuum fluctuations between them being slightly different from the fluctuations outside. In other words, virtual particles can push, they can shift energy, they can curve space. They're not fiction, they're part of the plumbing of reality. It's tempting to ask, are they real? But in quantum physics, that question misses the point. They're not observable entities. They're mathematical consequences of treating the universe as a set of quantum fields. And yet without them, the forces that govern every atom, every interaction, fall apart. They are the silent intermediaries in the constant negotiation of the cosmos. Next, we'll explore how physicists learn to visualize these invisible exchanges with an ingenious invention that transformed physics forever, the Feynman diagram. Feynman diagrams, how to picture particle interactions. If quantum electrodynamics is a conversation between particles, then the language it's spoken in is math, dense, multidimensional, brutally precise math. But in the 1940s, one physicist did something radical. He turned those invisible interactions into pictures. His name was Richard Feynman. A brash, brilliant mind with a gift for seeing through the fog of abstraction. And what he invented changed physics forever. He created Feynman diagrams, visual tools that let physicists track, analyze, and even intuit the bizarre choreography of particle interactions. At first glance, they look simple: lines, squiggles, intersections, like doodles on a napkin. But underneath, they represent complex quantum events. Every arrow, a particle; every vertex, an interaction; every loop, a calculation. Here's the basic idea. In a Feynman diagram, time flows from left to right, and space runs vertically, though these axes are often treated loosely. Straight lines usually represent matter particles, like electrons or quarks. Wavy lines are force carriers, photons, gluons, or WZ bosons. When two lines meet at a vertex, it means particles are interacting. Maybe one emits a photon, maybe two particles scatter off each other. Each vertex encodes a mathematical rule, a contribution to the total probability. Now, this is where it gets interesting. In quantum field theory, a process doesn't have just one path. It has all possible paths, and each contributes to the total result. Feynman diagrams let physicists visualize each path. You don't just have one diagram for an electron repelling another. You have a series of diagrams, each representing different ways the interaction could occur. The simplest one might show a single photon exchange between them. But more complex diagrams include loops, where virtual particles are emitted and reabsorbed, or even split and recombine. Each of these adds a correction to the calculation, a slight tweak in the final answer. And it's not just guesswork. There are rules for how to translate a diagram into a mathematical expression. It's like a language, where each line and point corresponds to a number, an integral, a constant. Physicists add up the contributions from every allowed diagram, and the total gives a prediction. This might sound like an artistic convenience, a shortcut to understand what's really happening underneath. But Feynman diagrams are more than metaphors. They are the math. They encode the entire structure of quantum interactions: the probability, amplitudes, the conservation laws, the dynamics of exchange. And they revealed something astonishing. Even the most complex quantum interactions could be boiled down to a sum over simple pictures. Instead of drowning in 10 pages of algebra, you could draw a squiggle and compute. It was a revolution. Here's a real-world analogy. Imagine trying to calculate every possible route from your house to the grocery store, including traffic, construction, detours, even alternate universes where the roads bend differently. Now imagine someone gives you a map, and every possible route is drawn out with a little cost next to it. That's what Feynman diagrams are to quantum field theory. They make the impossible tractable. This idea didn't just make QED work, it became the backbone of all modern particle physics. From the weak nuclear force to the strong force, to hypothetical new particles, Feynman diagrams are how physicists make predictions. Even today, when designing experiments at CERN or analyzing cosmic rays, scientists draw these diagrams to model the interactions they expect to see. They're not just shorthand, they're a window into a world that can't be seen directly, only computed, inferred, or glimpsed in the debris of particle collisions. There's something poetic about it. At the smallest scales, the universe doesn't give us clear answers, just probabilities, paths, uncertainties. But out of that fog, Feynman gave us pictures. And those pictures told stories of particles meeting, exchanging, vanishing, appearing, of a hidden order beneath the chaos. But these diagrams, as powerful as they are, didn't fix everything. Because with each loop you add to the diagram, the math becomes messier. The predictions explode with infinities, and solving that, learning how to renormalize the madness, was the next great hurdle QED had to clear. That's where we're headed next. Renormalization, making sense of infinities. Physics, at its best, is supposed to be precise. You plug in the numbers, run the math, and get results that match the real world, to 10 decimal places, if you're lucky. But in the early days of quantum field theory, this precision broke down. Not because the theory didn't work, but because it worked too well. Physicists began calculating the self-energy of an electron, the contribution of its own electric field to its mass. And the answer? Infinity. Not a big number, not a number with lots of digits. An actual mathematical divergence. The equation said the electron should weigh more than the entire universe. Clearly, something was wrong, and yet, experiments said otherwise. Electrons have a finite, tiny mass. So the theory had to be missing something, or interpreting it wrong. This was the crisis. How do you build a predictive, testable theory of quantum fields when the math collapses into infinities? The solution, surprisingly, was not to eliminate the infinities, but to tame them. That's the idea behind renormalization. Let's break this down. In quantum field theory, particles like electrons interact with their own fields constantly. Even in a vacuum, they're surrounded by virtual particles, photons blinking in and out of existence, tiny feedback loops from their own presence. These loops are the source of those infinities. Imagine trying to calculate the energy of an electron, but every time you account for one interaction, you uncover another, smaller one, and another nested inside that, and so on, a bottomless Russian doll of quantum effects. If you try to sum it all, the numbers diverge. But here's the trick. You don't need to calculate the absolute mass or charge of an electron from scratch. What matters is the difference between what you observe and what the theory predicts, and how that difference behaves under new conditions. Renormalization works by introducing bare values, theoretical placeholders for mass and charge, and absorbing the infinities into those. It's like saying, we don't know what the electron's mass is without quantum corrections, and we don't need to. We only need to measure it once, then use the theory to predict everything else. The infinities are swept into the constants, and all observable predictions become finite and testable. If this feels like sleight of hand, you're not alone. Even some of the pioneers of quantum theory were uncomfortable with it. Paul Dirac once said that renormalization was a sign that the theory wasn't fully understood. Feynman himself called it a dippy process. But the proof is in the numbers. Once renormalized, QED could predict the magnetic moment of the electron with insane precision, agreeing with experiments to better than 1 part in a billion. That level of accuracy doesn't happen by accident. It means the method, weird as it is, works. Here's a metaphor. Imagine you're trying to figure out how much a book weighs. But every time you weigh it, you're also including the weight of the scale itself, and the air, and the table, and the vibrations in the room. So instead of measuring the book in isolation, which you can't, you just measure the total, subtract the known background, and call the result your effective book weight. You never get to see the pure object, but you get a consistent number you can work with and use to make future predictions. Renormalization is that subtraction process, accounting for the messy, nested background noise of the quantum vacuum. The real triumph of renormalization wasn't just solving QED's infinities. It was creating a new way to think about scale. You don't need to know what happens at every level of energy to make accurate predictions at a given scale. You can treat the low-energy behavior as its own consistent world, and then run the constants if you need to shift up or down. This concept laid the groundwork for the renormalization group, a framework that now underpins quantum chromodynamics, the weak interaction, and even some areas of condensed matter physics. So in a strange way, the infinities turned out to be a gift. They forced physicists to invent new tools, and those tools revealed deeper patterns. The universe, it turns out, isn't free of chaos, but if you learn how to subtract just right, you can still find something stunning underneath. Next, we'll see how this subtracted theory, QED, became the most accurate physical theory we've ever built. A theory so precise, it can predict what happens in the 12th decimal place. The most accurate theory ever, predicting electron magnetic moments. In science, precision is everything. And quantum electrodynamics, QED, isn't just accurate, it's so accurate, it borders on surreal. Consider this. QED can predict the magnetic moment of the electron, a tiny correction to how it behaves in a magnetic field, to 12 decimal places. That's a level of agreement between theory and experiment that has never been matched in the history of physics. But why is this so important? What is a magnetic moment, and why does it matter that we can predict it so precisely? Let's unpack it. Every electron behaves like a little spinning charge, a quantum object with spin. This spin gives rise to a magnetic field, as if the electron were a tiny bar magnet. But here's the twist. When physicists first measured the magnetic behavior of electrons, they found that it wasn't quite what classical theory predicted. Quantum mechanics, and specifically the Dirac equation, predicted a G-factor of exactly 2. But experiments showed that the value was slightly larger, a discrepancy of about 0.1%. That might seem tiny, but in physics, small discrepancies are loud. They scream that something deeper is going on. And that something turned out to be virtual particles. Electrons don't just spin in isolation. They are constantly interacting with their own quantum field. They emit and reabsorb virtual photons, interact with vacuum fluctuations, and are surrounded by a cloud of possibility. All of that activity shifts the magnetic behavior, producing what's called the anomalous magnetic moment. Calculating that shift requires summing an infinite series of Feynman diagrams, each more complex than the last. Loops upon loops, corrections to corrections, each diagram contributing a tiny piece. This is where renormalization becomes essential. Without it, the diagrams yield nonsense. With it, the corrections stack into a precise prediction. The current best theoretical value for the electron's magnetic moment comes from QED calculations that include over tens of thousands of terms. Meanwhile, experimentalists have used techniques like penning traps, devices that confine a single electron in a magnetic field, to measure the actual value with staggering precision. The result? Theory and experiment agree to better than 1 part in 1 trillion. That's like measuring the circumference of the Earth and being accurate to within the width of a human hair. It's not just impressive, it's unprecedented. But this is more than just a math flex. It tells us something profound about the universe. That QED built on quantum field theory, virtual particles, and renormalized infinities actually describes reality. Not approximately, not metaphorically, but to a degree that challenges our very idea of what real means. If the universe were a machine, QED would be the service manual, down to the last bolt. Here's an analogy. Imagine trying to predict the outcome of flipping a coin 10 trillion times and getting it right every time. That's what QED has done with the electron. No other theory, not general relativity, not thermodynamics, not even the rest of the Standard Model, has achieved that level of agreement between theory and observation. And this isn't just about electrons. QED also predicts things like the Lamb shift in hydrogen, vacuum polarization, and scattering amplitudes in high-energy experiments. Every time it's tested, it holds. Even the design of technologies like MRI machines and semiconductors relies on QED-level accuracy. So this isn't just theoretical. It touches daily life. There's something humbling here. A theory built on weirdness, where particles talk to each other by borrowing energy from nothing, where space is never empty, where the math sometimes explodes and has to be tamed, has turned out to be the most precise tool in the physicist's toolkit. It tells us that precision doesn't always come from simplicity. Sometimes it comes from understanding the deep complexity underneath. But the story doesn't end with electrons. Because if light and matter can interact with such subtlety, what happens when light becomes matter? In the next part, we'll explore a process that feels like pure alchemy, where energy turns into particles, and particles into pure light, antimatter and pair production. Antimatter and pair production. Light turning into particles. If you ever wanted proof that the universe has a flair for the dramatic, consider this. Light can become matter, not metaphorically, not symbolically, literally. Under the right conditions, a beam of pure energy, light, can transform into particles with mass. This is called pair production, and it's one of the most astonishing predictions of quantum electrodynamics. It means that the universe isn't made of stuff, in the usual sense. It's made of energy that behaves like stuff, and sometimes decides to wear a particle costume. Let's start from the beginning. In 1905, Einstein's famous equation, E=mc², showed that mass is a form of energy. That idea turned physics on its head. Until then, mass and energy were treated as separate currencies. Mass was the solid, dependable thing. Energy was what made mass move or heat up. But Einstein showed they're convertible. So if mass can become energy, as in nuclear reactions, then logically, energy should be able to become mass. That's exactly what happens in pair production. Here's how it works. Imagine a high-energy photon, a particle of light. If that photon passes near the electric field of a nucleus, it can transform into a pair of particles, an electron and its opposite twin, the positron. This isn't just magic. It's required by the rules of quantum field theory. The photon's energy is converted into the mass of the two particles, plus a little extra to satisfy conservation of momentum and energy. Why near a nucleus? Because the process needs a third party to balance the books. The nucleus absorbs some of the momentum, so the laws of physics stay intact. This isn't rare. It happens in high-energy astrophysics, in the upper atmosphere during cosmic ray collisions, and in particle accelerators all the time. It's not theoretical. We've seen it. We've even done the reverse, smashed electrons and positrons together, watched them annihilate, and measured the resulting photons. But where does the positron come from? This is the truly weird part. The positron is an antiparticle, identical to the electron in mass and spin, but with the opposite electric charge. Its existence was predicted by Paul Dirac in the 1920s, almost as an accident. Dirac was trying to reconcile quantum mechanics with special relativity, and he found an equation that allowed for negative energy solutions. Rather than throw those away, he proposed they might represent a new kind of particle. That idea sounded crazy, until 1932, when Carl Anderson discovered the positron in cosmic rays using a cloud chamber. The prediction was right. Suddenly, antimatter was real. Every particle in the Standard Model has an antiparticle. The proton has the antiproton. The neutron has the antineutron. Even the neutrino might have an anti-self, though that's still under debate. These antiparticles are not imaginary. They're produced in natural processes and in the lab. They behave just like their counterparts, until they meet them. Because when a particle and its antiparticle collide, they annihilate, releasing all their mass energy as photons. It's not just destruction, it's perfect conversion. Mass to energy, energy to mass. Here's a real-world analogy. Think of particles and antiparticles as matter and antimatter versions of coins. Each has equal value, Opposite signs. If you bring $1 and -$1 together, they cancel and release energy equal to their total value. This process is the key to understanding why the universe has structure. Because in the early universe, just after the Big Bang, particles and antiparticles should have existed in equal numbers, but something tipped the balance. For every billion pairs that annihilated, one extra particle survived. That leftover matter is everything we see today: stars, planets, life. Without pair production and annihilation, there would be no structure, no atoms, no you. Today, antimatter is used in practical technology, like PET scans in medicine. It's created in accelerators and studied in labs, but it's incredibly difficult to store. Touch matter, and it's gone, but the concept remains powerful. It tells us that mass is just frozen energy, and that the vacuum of space, under the right conditions, can bloom with matter. In the next section, we'll explore why QED matters far beyond particle physics. In the chemistry of life, the electronics of your phone, and the structure of everything around you. Why QED matters. Technology, chemistry, and deep structure. Quantum electrodynamics might sound like a theory reserved for particle accelerators and Nobel Prize winners. But if you're reading this on a screen, flipping a light switch, or even breathing, you're living inside its predictions. QED isn't just the theory that describes how light and matter interact. It's the mathematical architecture of everything visible, from atoms and molecules to circuits and chemistry. So let's bring this all the way home. Start with the simplest atom. Hydrogen. 1 proton, 1 electron. That's it. But even that simplicity hides a storm of complexity. The electron doesn't orbit the nucleus like a tiny planet. It exists in a cloud of probability, constantly jostled by virtual photons, surrounded by vacuum fluctuations. The exact energy levels of that electron, the lines you see in hydrogen's spectrum, are shifted ever so slightly by these quantum effects. This tiny shift, called the Lamb shift, was one of the early experimental confirmations of QED. It showed that even the quietest atom buzzes with invisible quantum corrections. Without QED, we wouldn't be able to calculate these shifts. With it, we can predict them with astonishing precision. Zoom out to chemistry. Chemical bonds, the things that hold molecules together, are electromagnetic interactions between the electrons of different atoms. But electrons don't just sit politely in orbitals. They repel, entangle, tunnel, and dance with each other through QED-governed dynamics. Even phenomena like van der Waals forces, the weak attractions between neutral molecules, emerge from QED's description of fluctuating fields. These tiny forces determine whether a gecko can stick to a wall, or how proteins fold in your body. No QED, no biochemistry. Take a step further. Solid-state physics. The behavior of electrons in metals, semiconductors, and insulators. Everything from transistors to solar panels is based on how electrons move in potential fields. These movements are affected by quantum corrections. QED helps explain how electrons interact with each other, how they respond to external fields, and how even the vacuum shifts the energy landscape. For example, the Casimir effect, where two metal plates in a vacuum attract each other, is a pure QED effect. It comes from the difference in vacuum energy between inside and outside the plates. This isn't hypothetical, it's been measured. And the effect must be accounted for in designing nanotechnology, where forces at the quantum scale become significant. And of course, electronics. Your phone works because of transistors. Transistors work because of band structure. Band structure comes from how electrons interact with periodic potentials. A quantum behavior, shaped by QED's subtle fingerprints. Even the LED screen you're looking at emits photons from semiconductors. Those photons are released when electrons drop energy levels, a process governed by electromagnetic transitions predicted by QED. So yes, when you press a button on your device, you're participating in a controlled, microscopic application of quantum electrodynamics. But there's something deeper here. QED revealed a new way to think about reality. Before it, we imagined particles as tiny, solid balls interacting through invisible fields. After QED, we see the universe as a set of quantum fields, where particles are just ripples, and interactions are exchanges of information through those ripples. The distinction between real and virtual became less important than the outcome. How things behave, not what they fundamentally are. This changed how we build theories. Instead of trying to model nature with neat mechanical analogies, we now embrace its probabilistic, fluctuating, dynamic core. And we do it with mathematics so powerful, it matches the real world to parts per trillion. So why does QED matter? Because it works. It doesn't just describe the world, it builds it. It tells us that reality is made of interactions, not objects, that the void is not empty, that even in stillness, the universe hums. And this theory, this whisper between light and matter, touches everything from the structure of your body to the screen in front of you. But QED is only one part of a much larger story. There are other forces, other fields, other mysteries, and some of the biggest ones are invisible. Because as precise as our models are, they describe only a tiny fraction of what the universe is made of. 95% of reality is still missing, not a rounding error, a cosmic blind spot. So in the next episode, we'll step into that dark unknown. We'll follow the clues left by galaxies, supernovae, and the deepest silence in the sky, as we try to understand dark matter, dark energy, and what it means to know almost nothing about almost everything. If this journey made you think differently about what's beneath the surface of things, take a second to let us know, in the comments, what part hit you the hardest. And if you want to keep pulling on these threads, don't forget to like, subscribe, and join us again, right here on Overthinker.